Hello there, and welcome to Midnight Wanderer. Have you ever gazed up into the deep, dark velvet of a country sky, far from the glow of city lights, and seen that faint, shimmering cloud of light stretching from horizon to horizon? What if I told you that you're not just looking at a cloud, but into the very heart of a cosmic city, a city of 400 billion suns, and that you're looking at it from the inside? That soft band of light is our home, the Milky Way, and its peaceful expanse holds within it the story of everything we are and everything we have ever known. Tonight, there is nothing you need to do and nothing you need to solve. We're simply going to drift through this river of starlight, exploring its quiet wonders and gentle mysteries. You have permission to let go of the day, to release any thoughts that may be weighing upon you. Just allow my voice to be a soft current, carrying you along this peaceful journey. Let your body grow heavy, your breath slow and steady. There is only this moment, and the quiet wonder of our home galaxy. Before our journey begins, I'd love to know where in the world you're settling in from this evening, and what time it is for you. You can share it in the comments below if you feel so inclined. It's a lovely way to feel connected to this quiet community of fellow wanderers. And if you find a sense of peace in these explorations, a gentle like helps other curious minds find their way to this calm harbour as well. Now, let us begin. Let us begin our journey by finding our own place in this immense cosmic tapestry. Before we venture into its deepest mysteries, we will first find the comfort of our own home address, a familiar starting point in the quiet, swirling city of stars. Our story begins with a name that is as ancient as human curiosity itself, the Milky Way. Long before we knew what it truly was, people from every corner of the world would look up and see that same ethereal path painted across the night. To the ancient Greeks, it was a stream of celestial milk spilled by a goddess to nourish a hero. To the Romans, it was a road, the Via Lactea, a path for souls to travel. In the traditions of the Eastern world, it was the Silver River, a shimmering boundary separating two lovers represented by the stars Vega and Altair, who could only cross once a year. For the indigenous peoples of the Americas, it was the path of spirit animals or the backbone of the sky. For countless generations, this was its identity, a beautiful, unknowable feature of the heavens, a source of myth and wonder. It was a part of the human story, woven into the very fabric of our earliest attempts to understand our place in the universe. It was only much, much later, with the invention of the telescope, that we began to understand the true nature of this celestial river. When Galileo first pointed his simple instrument towards it, he was astonished to find that the hazy cloud was not a cloud at all. It was resolved into an uncountable multitude of individual stars, each one a distant sun, their light blurring together across the vast distances of space. The beautiful illusion of a milky river was shattered, only to be replaced by a truth that was even more profound and awe-inspiring. We were living inside a great flattened city of stars. The reason it appears as a band across our sky is because we are looking at this city from within its suburbs. Imagine you are standing in the middle of a vast flat field filled with millions of fireflies. If you look straight up or straight down, you see only a few. But when you look toward the horizon, across the widest part of the field, the lights of all those distant fireflies merge into a continuous, brilliant glow. Our view of the Milky Way is just like this. We are looking across the great flat disk of our galaxy, seeing the combined hazy light of billions of suns that are too far away to be seen individually. So, the name, born from ancient poetry and myth, remains. It is still a river, but now we know what its waters are made of. A flowing, gentle current of starlight, carrying us all on its silent cosmic journey. Having understood the grand vision of the galactic river, let us now gently zoom in, past the billions of distant suns, to our own small, peaceful corner of this cosmic city. If the Milky Way is a bustling metropolis, our solar system does not reside in its chaotic downtown core. Instead, we live in a quiet, unassuming suburb. Astronomers call this region the Orion Arm, or sometimes the Orion Spur. It isn't one of the grand major spiral arms of the galaxy, those brilliant highways of stellar traffic where new stars are being born in a constant, beautiful frenzy. Rather, it is a smaller, partial arm, a kind of peaceful side street nestled between two of the larger, more active arms, the Sagittarius arm and the Perseus arm. This location is one of the reasons our corner of the galaxy is so hospitable. We are far from the intense radiation and gravitational disturbances of the galaxy's crowded centre. We are also not in the thick of the major spiral arms, where nearby supernova explosions would be a more frequent and dangerous occurrence. Our neighbourhood is, in a cosmic sense, wonderfully calm. The stars here are more spread out, the cosmic traffic is lighter, and our sun can travel on its long orbit in relative peace. Think of it like living in a quiet valley between two vast, thundering mountain ranges. We can see the magnificent peaks, the bright, dense star fields of the major arms, in our night sky. But we are shielded from their most extreme weather. This peaceful location has given our world the immense, unbroken stretches of time needed for life to emerge and evolve. We are tucked away, safely and quietly, in a gentle cosmic haven, a perfect place from which to gaze out at the grander, more dramatic structures of our galaxy without being caught up in their turmoil. It is from this serene vantage point that our entire journey of understanding begins. From our quiet neighbourhood, it is easy to feel as if we are perfectly still, anchored in the silent dark. But this stillness is a profound illusion. Just as the Earth orbits the Sun, our entire solar system is on an immense and graceful journey of its own, orbiting the centre of the Milky Way galaxy. We, and everything we have ever known, are passengers on a great, cosmic merry-go-round. This is not a frantic, dizzying ride, but a slow, majestic, and almost silent dance that takes place on an unimaginable scale. Our Sun, along with its family of planets, is moving through the galaxy at a breathtaking speed. Yet because everything in our local area, the nearby stars, the clouds of gas and dust, is moving along with us, we feel no sense of this incredible motion. It is like being on a perfectly smooth train, where the only way to know you are moving is to look out the window at the landscape slowly passing by. In our case, the landscape is the backdrop of distant galaxies, the only truly fixed points in our cosmic view. This grand orbit is so vast that it takes our solar system approximately 230 million years to complete a single trip around the galactic centre. This immense span of time is known as one galactic year, or cosmic year. To put that into perspective, the last time our solar system was in this same position in its orbit, dinosaurs were just beginning to walk the Earth. The time before that, the world was a barren place, long before the flourishing of complex life. The entire history of humanity, from our earliest ancestors to this very moment, has taken place in just a tiny fraction of a single galactic year. We have travelled less than 1/1200th of our way around the galaxy since modern humans first appeared. This motion is a gentle reminder of the deep, slow rhythm of the cosmos. We are being carried silently and securely, on a journey that began long before us and will continue long after we're gone, a slow, clockwise waltz around the brilliant heart of our home galaxy. Let us linger for a moment on this idea of our journey around the galaxy and gently try to grasp the speed at which we are being carried. While the galactic year feels immeasurably slow from our human perspective, the actual velocity of our solar system is anything but. We are moving at an average speed of about 828,000 kilometers per hour, or about 230 kilometers every single second. This is a speed that is almost impossible to comprehend in earthly terms. It is a speed so immense that you could travel the entire circumference of the Earth in just a few minutes. And yet, as you lie here, settling into a state of rest, you feel absolutely nothing of this motion. You do not feel the Earth spin, you do not feel its orbit around the Sun, and you certainly do not feel its journey through the Milky Way. This creates a beautiful and calming paradox. We are simultaneously in a state of profound rest and incredible breakneck motion. Imagine being on the smoothest, most silent boat imaginable, drifting on an impossibly vast and calm ocean at night. You're lying on the deck looking up at the stars, and you feel no rocking, you hear no engine, you sense no movement at all. You feel perfectly still. But if you could somehow see the distant shores, you would realize you are crossing the ocean at an incredible speed. Our journey through the galaxy is just like this. We are held in a state of perfect inertial peace, where all the forces are so balanced and the scale so vast that we are completely unaware of the cosmic speeds we are travelling. It is a testament to the seamless elegance of the universe's laws. We are hurtling through the cosmos, yet we are held in a state of perfect, unshakable calm, safely cradled in the gentle, flowing current of the galaxy. For much of human history, we believed we were at the centre of everything. We thought the Earth was the centre of the solar system, and for a time, we imagined our solar system was at the centre of the galaxy. It is a natural human impulse to see ourselves as the focus of the grand design. But the quiet truth of the cosmos has always been one of humbling perspective. Just as we learned that the Earth orbits the Sun, we also learned that our Sun is not in a position of any special importance within the Milky Way. We reside about 27,000 light-years away from the galactic centre. To put that into perspective, if you were to imagine the entire Milky Way galaxy as a vast sprawling city, we would be located in a comfortable middle-ring suburb about 2/3 of the way out from the bustling, brilliant downtown core. This distance is, once again, a blessing. The galactic centre is a place of incredible energy, density and danger. The stars there are packed together thousands of times more densely than in our neighbourhood. Radiation levels are extraordinarily high, and at the very heart of it all lies a supermassive black hole, a gravitational titan that we will visit from a safe distance later in our journey. Our location provides a perfect balance. We are close enough to the galaxy's richness that our region is seeded with the heavy elements, the carbon, the oxygen, the iron, forged in previous generations of stars. These are the elements necessary to form rocky planets and ultimately life itself. Yet, we are far enough away to be shielded from the most intense and life-inhibiting radiation from the galactic core. Our position is a quiet testament to the fact that the most interesting places in the universe are not always at the centre of the action. Sometimes they are in the peaceful, gentle stretches in between, where the conditions are just right for quiet, complex stories to unfold over billions of years. Our distance from the centre gives us a beautiful, panoramic view of our cosmic city, allowing us to appreciate its grandeur without being overwhelmed by its intensity. Now that we understand our position within the galaxy, let us visualise its overall shape. The Milky Way is, for the most part, incredibly flat. The vast majority of its stars, gas and dust are contained within a structure called the galactic disk. This disk is immense in its diameter, stretching over 100,000 light-years across, but it is, in comparison, remarkably thin. While there is some debate, the main disk where we reside is only about 1,000 light-years thick. To make this scale feel more tangible, imagine that the entire Milky Way galaxy were the size of a large dinner plate. On that scale, the thickness of the galactic disk would be less than the thickness of a single sheet of paper. We, and our Sun, and nearly every star you can see with the naked eye, exist within this incredibly thin, shimmering plane. It is like living inside a single groove of an immense cosmic record. This is the reason, as we discovered earlier, that the Milky Way appears as a band of light in our sky. We are looking out from within this flat plane, seeing its structure edge on. This disk is not a solid object, of course. It is a swirling, dynamic system of stars, gas clouds and dust, all held together by gravity and orbiting the central core in a slow, majestic rotation. The beautiful spiral arms, which we will explore soon, are patterns of density that ripple through this disk, much like the patterns that form in a shallow pool of water when a stone is dropped into it. Understanding this incredible flatness, this shimmering, paper-thin disk on a cosmic scale, is the key to mapping the rest of our galaxy's structure. It is the foundation upon which everything else is built. Since we live inside this thin, crowded and often dusty galactic disk, our view in certain directions is obscured. When we look directly into the plane of the Milky Way, towards that shimmering band in the night sky, we are looking through a thick forest of stars, gas and dust. This cosmic dust acts like a fog, blocking the light from more distant objects and making it difficult to see what lies on the other side of the galaxy, or even what lies at its very centre in visible light. So, how do astronomers get a clear view of the universe beyond our own galaxy? They do what anyone would do if they were trying to see past a forest. They look up. By directing their telescopes up or down, perpendicular to the galactic plane, they are looking out of the thinnest part of the disk. The view in these directions is much clearer, less cluttered. There is far less gas and dust to block the light, and it is in these clearings, these cosmic windows, that we can get an unobstructed view of the distant universe. This is where the Hubble Space Telescope took its famous deep-field images, staring for days at a seemingly empty patch of sky to reveal thousands of distant galaxies. It chose a window out of our own galactic plane to do so. Think of our galaxy as a house with very dusty windows. If you try to look through the living room window to the street, the view is hazy. But if you go to the attic and look out the skylight, your view of the sky above is perfectly clear. Astronomers use these galactic skylights to study the grander cosmos, reminding us that even our vast galaxy is just one island in an even more immense cosmic ocean. Our journey through the basic structure of the Milky Way is not yet complete. We have explored the thin, shimmering disk where we live, but our galaxy is much larger and more mysterious than that. Surrounding the entire disk like a vast ghostly sphere is the galactic halo. If the disk is a bustling flat city, the halo is the enormous, quiet, and almost empty countryside that extends for hundreds of thousands of light years in every direction. It is the true atmospheric boundary of our galaxy. This halo is not empty. It is sparsely populated with very old stars and ancient dense star clusters, known as globular clusters, which we will visit later. These are some of the very first stars to have formed in the Milky Way's history, and they orbit the galactic centre in long, looping elliptical paths, far above and below the orderly rotating disk. They are like ancient lonely ghosts on the outskirts of the city, holding the memory of the galaxy's earliest days. Seeing them is like finding ancient forgotten ruins far outside a modern metropolis. But the stars and clusters of the halo make up only a tiny fraction of its mass. The vast majority of the halo is made of something else entirely, something we cannot see, the mysterious substance known as dark matter. This is the great invisible scaffold upon which our entire galaxy is built. While the disk contains the bright visible matter, the halo contains the immense, unseen mass that generates the gravity needed to hold everything together. Without the gravitational influence of this dark matter halo, the stars in the outer parts of our galaxy would be moving so fast that they would simply fly off into intergalactic space. The galaxy would spin itself apart, so the halo is like a vast invisible sponge, and the stars and gas of the disk are like water held within its structure. We cannot see the sponge itself, but we know it must be there because of the way it holds the water. This halo is where most of the galaxy's mass resides, a silent, invisible, and profoundly powerful presence that envelops us completely. It is the final and largest piece of our galactic home, a spherical kingdom of old stars, ancient memories, and an enduring quiet mystery. Now that we have a sense of our personal place within this cosmic structure, let us gently pull our perspective back to see the Milky Way not as our immediate neighbourhood, but as a single, magnificent piece of cosmic architecture. We will now admire its grand design. For a long time, astronomers believed the Milky Way was a simple spiral galaxy, like its famous neighbour, Andromeda, a beautiful, swirling pinwheel of stars with arms that curved all the way into the very centre. However, as our methods of observation have become more sophisticated, allowing us to peer through the obscuring dust, a different and more interesting picture has emerged. Our galaxy is what is known as a barred spiral galaxy. This means that at its very heart, there isn't a simple, spherical cluster of stars. Instead, there is a dense, elongated, bar-shaped structure composed of billions of older, mostly reddish stars. This central bar is enormous, stretching for about 27,000 light-years from end to end. Coincidentally, its length is about the same as our distance from the galactic centre. From the two ends of this brilliant glowing bar, the grand spiral arms of the galaxy emerge and begin their graceful curving journey outwards. Imagine a spinning lawn sprinkler. A simple spiral galaxy is like a sprinkler with curved arms that go all the way to the central pivot. A barred spiral galaxy, like our own, is more like a sprinkler that has a single, straight, rotating piece in the middle, with the curved arms beginning at the very ends of that straight piece. This bar is not just a cosmetic feature, it is a critical part of the galaxy's engine. It acts as a great cosmic channel, funneling gas and dust from the spiral arms inward towards the galactic centre. This process can feed star formation in the region around the bar and, over immense timescales, provide fuel for the supermassive black hole that resides at its very heart. Discovering this bar was like finding the hidden blueprint of our cosmic city. It showed us that our galaxy has a more complex, more dynamic, and more elegant structure than we had ever imagined, with a brilliant, shining bar of stars at its core from which all its other splendours flow. Flowing gracefully outwards from the ends of the central bar are the grand avenues of our galaxy, its spiral arms. While our galaxy has many smaller spurs and minor arms, like the Orion arm where we reside, it is now believed to have 4 primary major spiral arms. 2 of these arms appear to be more prominent and richer in stars and gas than the other 2. The 2 main arms are called the Scutum Centaurus arm and the Perseus arm. These are the galaxy's great highways, blazing with the light of young, hot blue stars and glowing pink with the light of vast stellar nurseries. They are the most active and brilliant parts of the galactic disk. Attached to the central bar as well are 2 other less defined arms, known as the Norma arm and the Sagittarius arm. Our own Orion spur is located between the Sagittarius and Perseus arms. These arms are not solid structures. They are not like the spokes of a wheel with stars fixed to them. Instead, they are what we call density waves. Imagine a traffic jam on a highway. The jam itself moves very slowly, but individual cars move into it, slow down for a while, and then move out of it again. The spiral arms are like cosmic traffic jams. Stars, gas, and dust in their orbits around the galaxy move into these slow-moving density waves, get compressed together, and this compression triggers a flurry of new star formation. This is why the arms are so bright. They are constantly being lit up by newborn stars. So when we look at the spiral arms, we are not looking at a fixed structure, but a beautiful slow-motion ripple of creation constantly moving through the galactic disk. When we look at pictures of other galaxies, we are captivated by the brilliant light of their billions of stars. But just as important to the galaxy's life and structure is what lies in between them. The space within the spiral arms, and indeed throughout the galactic disk, is not empty. It is filled with a vast diffuse mixture of gas and dust, known collectively as the interstellar medium. This material is, in a very real sense, the soul of the galaxy. It is both the raw material from which new stars are born and the enriched remnants of stars that have died. The gas is primarily composed of hydrogen and helium, the lightest and most abundant elements in the universe, forged in the Big Bang. It is this hydrogen gas that, when compressed in the spiral arms, collapses under its own gravity to form beautiful nebulae, the stellar nurseries of the galaxy. The dust, however, is made of much smaller, more complex particles. It consists of tiny grains of silicates and carbon, essentially microscopic bits of sand and soot. This dust is created in the atmospheres of old, dying stars and scattered into space, where it mixes with the primordial gas. Though this dust makes up only about 1% of the interstellar medium's mass, its effect is profound. It is what blocks our view of the galactic centre, creating the dark rifts and lanes we see in the Milky Way's band of light. It's like a cosmic smoke that absorbs and scatters starlight, but it is also crucial for creation. These tiny dust grains act as sheltered surfaces where molecules can form, and they help cool the gas clouds, allowing them to collapse and form stars and planets more easily. So this interstellar medium is the galaxy's atmosphere, its reservoir of potential, and its memory. It is a soft, cloudy, and dynamic substance that fills the space between the stars, constantly being recycled in a gentle, galaxy-wide ecosystem of birth, life, and death. We have spoken of the galaxy's shape, its arms, and its components, but it is difficult to truly feel its scale. The numbers are so vast they can feel meaningless. We say that the main visible disk of the Milky Way is about 100,000 light-years across. But what does that truly mean? A light-year is the distance that light, the fastest thing in the universe, travels in a single year. That distance is about 9.5 trillion kilometres, or about 6 trillion miles, and our galaxy is 100,000 of those units wide. Let us try a more gentle metaphor. Imagine our entire, vast solar system, out to the orbit of Neptune, were shrunk down to the size of a single grain of salt. If you were to hold this grain of salt in your hand, representing our entire solar system, the Milky Way galaxy would be a sprawling city the size of North America. All the stars you see in the night sky with your naked eye would be other grains of salt, all within a few feet of you. The rest of the continent-sized city would be filled with the other 400 billion grains of salt, each a star system, most of them too far to be seen individually. Even this does not capture the full truth. Recent studies suggest that the galaxy may be much, much larger than we thought. If we include the vast, sparse halo of stars and, more importantly, the enormous, invisible halo of dark matter that surrounds it, the Milky Way's true sphere of influence might stretch for 2 million light-years. On our scale, where the solar system is a grain of salt, this would mean our galaxy's true size is not a city the size of North America, but a sphere so large it could comfortably hold the Earth and the Moon. This is the true scale of our home. It is a place of such profound size that it defies easy comprehension. It is so large that the light from a star on one edge of the galaxy takes 100,000 years just to reach the other side. When we look up at the band of the Milky Way, we are seeing starlight that has been travelling for tens of thousands of years to reach our eyes. We are looking at an image that is simultaneously in the present and in the distant past. This immensity is not meant to make us feel small, but to fill us with the sense of quiet, boundless wonder. We live within a structure so vast that it operates on scales of time and space that are almost eternal from our human perspective. Having contemplated the immense size of our galaxy, a natural next question arises. How much does it all weigh? How do you weigh a galaxy? It is a question that leads us directly to one of the deepest mysteries in all of cosmology. Astronomers can estimate the mass of the galaxy in a few ways. One method is to look at all the things we can see, the stars, the gas, the dust, and add it all up. We can estimate the number of stars and their average mass and measure the amount of gas and dust. When we do this, we arrive at a truly colossal number. The visible matter in our galaxy, the baryonic matter as it's called, adds up to about 200 billion times the mass of our Sun. But this is where the mystery begins. There is another way to weigh a galaxy, a way that is much more reliable. Isaac Newton taught us that the more massive an object is, the stronger its gravitational pull. We can measure the speed at which stars in the outer parts of the galaxy are orbiting the centre. The faster they are going, the more mass there must be in the centre of the galaxy, holding them in their orbits with its gravity. If there wasn't enough mass, these fast-moving stars would simply fly off into space. When astronomers did this, they found a shocking discrepancy. The stars on the outskirts of the Milky Way are moving far too quickly. They are moving so fast that the gravity from all the visible matter, all the stars, gas and dust we can account for, is not nearly enough to keep them in their orbits. In fact, there is not even close to enough. To explain the speeds of these stars, the galaxy must have about 6 times more mass than we can see. This means that about 85% of the total mass of our galaxy, the vast majority of its substance, is completely invisible to us. It does not shine, it does not reflect light, it does not interact with our instruments in any detectable way, except through its immense gravitational pull. This invisible mass, which so outweighs the brilliant stars and glowing nebulae, is what we call dark matter. The name is perhaps a little dramatic. It is called dark simply because it does not emit or interact with light. It is, for all intents and purposes, completely transparent. It is not dark in the sense of being a black cloud. It is dark in the sense of being utterly, perfectly invisible. This mysterious substance is the great unseen scaffold of our galaxy, and indeed of the entire universe. The best way to imagine its role is to think of a large natural sea sponge that has been soaked in water. When you look at the sponge, you see the water glistening, you see it held within the sponge's structure. But the sponge itself, the fibrous material that gives it its shape and holds the water, is the dominant structure. The luminous matter of our galaxy, the stars, planets and gas clouds that we can see, is like the water. The dark matter is the sponge. It forms a vast spherical halo, a cosmic framework that extends far beyond the visible disk of the galaxy. The gravity of this dark matter sponge is what holds all the shining, visible matter in place, allowing it to form into the beautiful spiral structure we observe. We do not yet know what dark matter is. It is one of the most profound and humbling mysteries in all of science. It is not made of atoms like you and I and the stars are. It is likely some new type of subatomic particle that we have not yet discovered, a particle that barely interacts with our world at all, except to exert its gentle, persistent gravitational pull. Its presence is a quiet and constant reminder that what we can see of the universe is only a tiny fraction of what is actually there. We're living in a galaxy whose true nature is mostly invisible to us, a city of light built within a much larger, quieter, and more mysterious city of transparent, unseen matter. Our tour of the galaxy's grand design now takes us back to its very heart, to a feature that lies at the centre of the galactic bar. This is the galactic bulge. If the disk is the flat, sprawling city, and the halo is the vast spherical countryside, the bulge is the old, dense, historic downtown core. It is a tightly packed, roughly spherical swarm of stars, tens of thousands of light years in diameter. Unlike the spiral arms, which are filled with young, hot blue stars, the galactic bulge is composed mainly of much older stars. Many of these stars are ancient red giants, giving the central region of our galaxy a soft yellowish golden glow. There is very little gas and dust in the bulge, and therefore very little new star formation is happening there. It is a quiet, settled, and ancient part of our galaxy. The stars in the bulge do not orbit the centre in the same orderly circular paths as the stars in the disk. Instead, they have more random, eccentric orbits, buzzing around the core like a swarm of bees. This central bulge is a place of incredible density. While in our neighbourhood we have only a handful of stars within a few light years of our Sun, in the galactic bulge, stars are packed in millions of times more tightly. The night sky from a planet in the galactic bulge would be a breathtaking, almost continuous blaze of light, with thousands of stars shining as brightly as the full moon does in our own sky. This ancient, golden, crowded core is the anchor of our galaxy, the gravitational heart around which the entire vast disk rotates. And at the very centre of this bulge, a final, deeper mystery awaits our exploration. Having admired the grand architecture of our galaxy, we now turn our attention to its inhabitants. A city is defined by its people, and a galaxy is defined by its stars. Let us drift now among the varied and beautiful stellar population of the Milky Way. Let us begin with a simple, humbling number. The Milky Way galaxy is home to an estimated 400 billion stars. The true number could be as low as 100 billion, or as high as 1 trillion, but 400 billion is a commonly accepted estimate. It is a number so large that our minds are not equipped to truly grasp it. If you were to try and count them, one star every second, without ever stopping to eat or sleep, it would take you over 12,000 years. To feel this number in a more gentle way, imagine you're standing on a vast quiet beach at night. Look down at the sand at your feet. Pick up a single handful of sand. The number of individual grains of sand in your hand is roughly the same as the number of stars you can see with your naked eye on the clearest night, about 5 to 10,000. Now, imagine all the sand on all the beaches in all the world. The total number of stars in our Milky Way galaxy is thought to be greater than the total number of grains of sand on all the beaches of planet Earth. Every single one of those stars is a sun. Many of them are similar to our own. Many are vastly larger and brighter, and many more are smaller and dimmer. And as we will soon explore, a great many of them likely have their own families of planets. So when you look up at the night sky, even at that faint milky band, you are not just looking at points of light. You are looking at a city of 400 billion suns, a population so vast that it whispers of endless possibility and an almost infinite number of quiet stories unfolding across the expanse of our cosmic home. In any great city, you will find inhabitants of all ages, from the newly born to the ancient. Our galaxy is no different. Among its 400 billion stars are some of the oldest objects in the entire universe. These ancient stars are like living fossils, having formed when the Milky Way itself was just beginning to assemble from primordial clouds of gas over 13 billion years ago. They are a direct shining link to the dawn of cosmic time. These oldest inhabitants are found mostly in two places, the galactic bulge at the centre and drifting through the vast spherical halo that surrounds the galaxy. They are not like our Sun. The very first stars were made of only the simplest elements created in the Big Bang, hydrogen and helium. All the heavier elements, like the oxygen we breathe and the carbon that forms our bodies, had not yet been created. They are forged only in the hearts of stars and in the explosions of their deaths. Because these ancient stars formed from this clean primordial gas, they are very poor in these heavier elements, which astronomers call metals. By measuring the amount of metal in a star's atmosphere, we can get a very good estimate of its age. The lower the metal content, the older the star. These ancient stars are typically smaller and cooler than our Sun, and many of them are red dwarfs, which we will meet shortly. Their old age and simple composition tell us the story of our galaxy's infancy. They are the quiet elders of our cosmic city, the first generation of inhabitants, and they have been shining their faint, steady light almost since the beginning of the universe itself, silent witnesses to nearly the entire history of the cosmos. By studying their gentle light, we're reading the earliest chapters of the Milky Way story. From the oldest residents of our galaxy, let us now drift to the very youngest. Let us visit the places where new stars are being born, right now, in this very moment. These places are called stellar nurseries, and they are among the most beautiful and serene objects in the cosmos. They are vast, cold clouds of interstellar gas and dust, known as nebulae. You have seen pictures of them, the Orion Nebula, the Eagle Nebula with its famous pillars of creation. They are ethereal, glowing clouds of cosmic colour. These nebulae are the galaxy's reservoirs of creative potential. They are mostly made of cold hydrogen gas. For millions of years, these clouds can drift peacefully through the spiral arms of the galaxy. But sometimes something will disturb them. A gravitational nudge from a passing star or a shock wave from a distant supernova explosion. This disturbance can cause parts of the cloud to begin to collapse under their own gravity. The process is like the way tiny droplets of moisture in a cloud on Earth gather together to form a single, heavy raindrop. As a clump of gas and dust in the nebula grows denser, its gravity increases, pulling in more and more material from the surrounding cloud. The core of this collapsing clump begins to heat up under the immense pressure. For thousands of years, this process continues, the core growing hotter and denser until something truly magical happens. The temperature and pressure at the centre become so extreme that nuclear fusion ignites. Hydrogen atoms begin to slam into each other with such force that they fuse together to form helium, releasing a tremendous amount of energy in the process. This is the moment a star is born. A new light ignites in the cosmos. The new star's radiation and stellar wind then blow away the surrounding gas and dust, revealing the newborn star and often its younger siblings, which have all formed from the same parent cloud. These nebulae are places of quiet, slow and gentle creation. They are the calm, beautiful wombs of the galaxy, where the dust of old, dead stars is patiently recycled into new light and new potential, in a cycle that has continued, unbroken, for over 13 billion years. When we look up at the night sky, our eyes are naturally drawn to the brightest and most magnificent stars. But these brilliant beacons are the great exception in the galactic population. They are the rare superstars. The most common type of star in the Milky Way is far more humble, far more quiet, and almost invisible to our eyes. They are the red dwarfs. It is estimated that a staggering 75%, or 3 out of every 4 stars in our galaxy, are red dwarfs. These stars are very small, typically having between 10% and 50% of the mass of our own Sun. Because they are so much less massive, the gravitational pressure at their core is lower, and so they burn their nuclear fuel much, much more slowly and at a much lower temperature. This is why they appear as a faint reddish-orange colour. They are the slow-burning embers of the cosmos, rather than the blazing fires. Not a single red dwarf is bright enough to be seen from Earth with the naked eye, despite there being billions of them. Our closest stellar neighbour, Proxima Centauri, is a red dwarf, and even it is far too dim to see without a telescope. What makes red dwarfs truly remarkable is their incredible lifespan. Because they are so frugal with their fuel, they can continue shining for an extraordinarily long time. Our Sun has a lifespan of about 10 billion years. A typical red dwarf will shine for trillions of years. That is 1,000 times longer than the current age of the universe. They are, for all practical purposes, eternal. Long after our Sun has burned out, long after the great blue giant stars have exploded, long after the galaxy has merged with Andromeda, the faint, gentle reddish glow of the red dwarf stars will still be illuminating the cosmos. They are the quiet, stable and enduring foundation of the galactic population, the silent majority patiently shining on through the deepest stretches of cosmic time. In beautiful contrast to the quiet, enduring red dwarfs, let us now turn our attention to the rock stars of the galactic population, the blue giants. These are the most massive and most luminous stars in the entire galaxy. They're incredibly rare, but their brilliance is so extreme that many of the bright stars we can see in our night sky, like Rigel in the constellation of Orion, are blue giants, even though they are hundreds of light years away. These stars are true behemoths, often containing dozens of times the mass of our Sun and shining with a light that is hundreds of thousands or even millions of times brighter. Their immense mass creates unimaginable pressure and temperature at their core, causing them to burn through their hydrogen fuel at a truly ferocious rate. This is what makes them so incredibly hot and gives them their characteristic brilliant white-blue colour. But this extravagant lifestyle comes at a cost. The brightest lights often burn out the fastest. While a red dwarf can live for trillions of years, a blue giant is lucky to last for a few million years. It is a cosmic blink of an eye. They live fast and die young. Their lives are short, brilliant, and incredibly important. It is in the fiery hearts of these massive stars and in their spectacular deaths as supernovae that the heaviest elements in the universe are forged. The oxygen in the air you're breathing, the iron in your blood, all of it was created inside a star like this, a star that lived and died long before our Sun was even born. So while they may be brief, their legacy is eternal. They are the great cosmic forges, the beautiful short-lived titans that seed the galaxy with the raw materials necessary for building planets and ultimately for building life. All stars, no matter how large or small, eventually run out of fuel. What happens next depends on the star's mass. For stars like our Sun, and for the vast majority of stars in the galaxy, the final chapter of their life is a quiet and graceful one. When a Sun-like star exhausts the hydrogen fuel in its core, it begins to swell dramatically, becoming a red giant. Our own Sun will do this in about 5 billion years, its outer layers expanding to possibly engulf the inner planets. After this phase, the star's outer layers will drift away into space, creating a beautiful glowing structure known as a planetary nebula. What is left behind at the centre is the star's collapsed, incredibly dense core. This remnant is called a white dwarf. It is a truly remarkable object. A white dwarf packs the mass of a Sun into a volume about the size of the Earth. A single teaspoon of white dwarf material would weigh several tons. A white dwarf no longer generates new heat through nuclear fusion. It is simply the cooling ember of a once mighty star. It shines only because it is still incredibly hot from its former life, like a piece of metal pulled from a forge that slowly radiates its heat away into the cold of space. Over billions and billions of years, a white dwarf will continue to cool and fade, its light slowly shifting from white to yellow to orange, and finally, after an almost infinite amount of time, it will become a cold, dark cinder of crystallized carbon and oxygen, a black dwarf. This is the peaceful, gentle end for most of the galaxy's stars, a slow, quiet fading into the final, silent darkness. It is not a violent death, but a long, graceful and serene retirement. While Sun-like stars fade away gracefully, the most massive stars, the blue giants we met earlier, end their lives in a far more spectacular fashion. When a star more than 8 times the mass of our Sun runs out of fuel, its core collapses under its own immense gravity in a fraction of a second. This catastrophic collapse triggers a rebound explosion of unimaginable power known as a supernova. For a brief period, often just a few weeks, a single supernova can outshine its entire host galaxy, blazing with the light of hundreds of billions of stars. It is the most powerful explosion the universe knows. But it is a mistake to think of a supernova as purely an act of destruction. It is, in fact, the universe's ultimate act of creation and recycling. In the moments of the core's collapse and the subsequent explosion, the conditions become so extreme that the heaviest elements in the universe are forged. Elements like gold, silver, platinum and uranium are created almost exclusively in the fires of a supernova. This incredible explosion then blasts all of these newly created elements, along with all the elements forged during the star's life, out into the galaxy at incredible speeds. The beautiful expanding clouds of gas and dust left behind by these explosions are called supernova remnants. This enriched material then mixes with the interstellar medium, seeding it with the heavy elements necessary for the next generation of stars and planets. The iron in the very structure of the Earth, the calcium in your bones, all of it was once part of a star that died in a supernova explosion billions of years ago. We are, in the most literal sense, made of stardust. A supernova is not an ending. It is a violent, beautiful, and necessary act of cosmic generosity, scattering the seeds of future creation across the galaxy. What is left behind after a supernova explosion? If the original star was massive enough, its core will collapse beyond the white dwarf stage into something even more extreme and bizarre, a neutron star. A neutron star is one of the strangest and most fascinating objects in the entire universe. As the core collapses, the gravitational force is so immense that it overcomes the forces that keep atoms separate. Protons and electrons are crushed together to form neutrons, packing an entire star's worth of matter into an unbelievably small space. A typical neutron star may have 1.5 times the mass of our Sun, but it is compressed into a sphere only about 20 kilometres, or 12 miles, in diameter. It is a city-sized object with the mass of a star. The density is almost beyond comprehension. A single sugar cube-sized piece of a neutron star would have the same mass as all of humanity combined. It is the densest form of matter in the universe, second only to a black hole. These objects are also born spinning incredibly rapidly, often rotating hundreds of times every second. They have unimaginably powerful magnetic fields. As they spin, they can emit beams of radiation from their magnetic poles. If one of these beams happens to sweep across our line of sight here on Earth, we see a regular pulse of energy, and we call the object a pulsar. A neutron star is the ghostly, ultra-compressed corpse of a massive star, a tiny, spinning, hyper-dense remnant that stands as a quiet monument to the incredible violence of its birth. It is a true ghost in the cosmic graveyard. We think of stars as being bound to their host galaxies, loyal citizens of their cosmic city. But our galaxy is not a closed system. It is possible for a star to be ejected from the Milky Way entirely, to be cast out into the immense, dark and lonely void between the galaxies. These are known as intergalactic, or hypervelocity stars. A star can be ejected in a few ways. One of the most common mechanisms involves a close encounter with the supermassive black hole at the centre of our galaxy. If a binary star system, two stars orbiting each other, passes too close to the black hole, the intense gravity can capture one of the stars while violently flinging the other one outwards at an incredible speed, like a stone from a slingshot. This speed can be so great that it exceeds the galaxy's escape velocity, meaning the star is no longer gravitationally bound to the Milky Way and will travel outwards forever. These lonely stars journey through the vast, empty darkness of intergalactic space. For billions of years, they will travel in near total isolation. The nearest other star might be millions of light years away. If such a star had planets, their inhabitants would look up at a sky that is almost completely black. There would be no constellations, no shimmering band of the Milky Way. The only lights would be the faint, fuzzy smudges of distant galaxies, unimaginably far away. It is a vision of profound and peaceful solitude. These wandering stars remind us that the universe is a dynamic and sometimes chaotic place, where even suns can be torn from their homes. They are silent travellers in the great emptiness, carrying their faint light into the vastest and quietest realms of the cosmos, a testament to the powerful gravitational heart of the galaxy they left behind. Our journey now takes us towards the most extreme, most crowded and most mysterious part of our entire galaxy. From a safe and gentle distance, we will now turn our gaze to the galactic core, the brilliant, chaotic and powerful heart of the Milky Way. As we journey inward from our peaceful suburban arm, the scenery of the galaxy changes dramatically. The space between the stars begins to shrink, and the density of the stellar population increases slowly at first, and then exponentially. As we approach the galactic centre, we enter a region where the stars are packed together thousands, or even millions, of times more tightly than in our own neighbourhood. The soft, dark night we are used to no longer exists here. If you were on a planet near the galactic core, the sky would be a solid, blazing wall of starlight. The combined glow of millions of nearby suns would be so intense that true darkness would never fall. The sky would shine with a perpetual brilliant twilight, brighter than 1,000 full moons. There would be no familiar constellations, only a dazzling, seamless tapestry of countless star points, so close together they would merge into a continuous golden haze. This overwhelming light comes from the billions of ancient stars that make up the galactic bulge, which we visited earlier. This is the oldest part of our cosmic city, a place where stars have been living and dying for over 12 billion years. The sheer concentration of light and energy here is hard to imagine. It is a place of incredible beauty, but also of intense radiation. This constant, overwhelming bath of starlight is the first sign that we are approaching a place of truly cosmic power, the very heart of our galaxy. It is the glow of the furnace at the centre of our cosmic city. Observing the galactic centre directly is incredibly difficult due to the thick veils of interstellar dust that lie between us and it. However, astronomers can use infrared and radio telescopes which can peer through this dust as if it were glass. When they do, they can observe the motions of the stars in the innermost region of the galaxy, and what they see is truly remarkable. In the very heart of the galaxy, within the space of just a few light months, there is a cluster of stars orbiting something invisible at incredible speeds. These are known as the S-stars. They are moving so fast and their orbits are so tight and elliptical that they look less like a stately cosmic dance and more like a frantic swarm of comets. One of these stars, named S2, completes a full orbit of the galactic centre in just 16 years. To do this, it must travel at speeds of up to 30 million kilometres per hour, or about 3% of the speed of light. This incredible, frantic dance is the key piece of evidence that tells us something extraordinary must be lurking at the very centre. For these stars to be held in such tight, fast orbits, they must be orbiting an object of truly immense mass and incredibly strong gravity. The laws of physics tell us that if you know the size of an orbit and the speed of the object in that orbit, you can calculate the mass of the object it is circling. By carefully tracking the paths of these S-stars over decades, astronomers were able to calculate the mass of the invisible object they were all dancing around. The answer was stunning, and it pointed to only one possible conclusion. The invisible object at the very heart of our galaxy, the object that these stars are so frantically orbiting, has a name. It is called Sagittarius A, pronounced Sagittarius A star. The name itself is a piece of history. The Sagittarius part comes from the fact that, from our perspective on Earth, the centre of the galaxy lies in the direction of the constellation Sagittarius. The A comes from the fact that it was the first and therefore brightest source of radio waves discovered in that constellation, and the asterisk, the star at the end, was added by the astronomer Robert Brown, who realised this radio source was something unique and special. He added the asterisk for the same reason a physicist would, to denote an excited state. This was a place of unusual energy. For a long time, Sagittarius A was simply a point of curiosity, a powerful but invisible source of radio waves at the galaxy's centre. We could not see it in visible light, but our radio telescopes could hear its faint static hum across 27,000 light-years of space. It was a mystery, a puzzle. What could be so small, so invisible, and yet so powerful? The answer came from combining this radio observation with the observations of the dancing S-stars. The radio source was located at the exact gravitational centre of all those frantic orbits. The source of the energy and the source of the immense gravity were one and the same. And there is only one known object in the universe that can be that massive, that small, and that invisible. The mystery of Sagittarius A has been solved. At the heart of our Milky Way galaxy resides a supermassive black hole. The calculations based on the orbits of the S-stars tell us that this object contains the mass of 4 million suns, all compressed into a space smaller than the orbit of Mercury. A black hole is an object whose gravity is so powerful that nothing, not even light, can escape its pull once it crosses a certain boundary. It is the ultimate endpoint of gravity. It is natural to imagine a black hole as a cosmic vacuum cleaner, aggressively sucking in everything around it. But this is not quite right. A black hole's gravity is just like any other object's gravity. It is just much, much stronger, because its mass is packed into such a small space. If you were to replace our Sun with a black hole of the same mass, the Earth and the other planets would continue to orbit it just as they do now, though in complete darkness. You have to get very, very close to a black hole to be in any danger. A gentler way to picture a black hole is to imagine space-time, the very fabric of the universe, as a stretched rubber sheet. A star or a planet creates a small dimple in this sheet, and other objects roll around in that dimple, which is what we feel as gravity. A supermassive black hole, however, is like placing an incredibly heavy cannonball on the sheet. It creates a deep, steep well, a sort of bottomless waterfall in the fabric of space-time. The S-stars are like objects swirling rapidly around the very edge of this waterfall. Our supermassive black hole is not a monster. It is the great silent anchor of our galaxy. Its immense gravity is the central pivot point around which the entire, vast city of 400 billion stars revolves in its slow, majestic dance. It is the quiet, invisible linchpin that holds our entire cosmic home together. Given that we have a 4 million solar mass black hole at the centre of our galaxy, one might expect it to be a place of incredible violence and destruction, with matter constantly screaming into its depths. But when we look at Sagittarius A, we see something surprising. It is, for a supermassive black hole, remarkably quiet. It is not what astronomers call an active galactic nucleus. Active galaxies have black holes at their centres that are furiously consuming vast amounts of gas, dust, roll, and stars. As this material gets pulled in, it forms a swirling, superheated disk around the black hole, known as an accretion disk. The friction in this disk heats the material to millions of degrees, causing it to shine with an incredible fierce light, often blasting out gigantic jets of energy that can be seen from across the universe. Our galaxy's centre shows very little of this activity. Sagittarius A seems to be on a starvation diet. There is not a lot of loose gas and dust in its immediate vicinity for it to feed on. It does occasionally snack on small clouds of gas, or perhaps an unfortunate star that wanders too close, which causes it to flare up with temporary bursts of X-rays and radio waves, but for the most part, it is dormant. It is a sleeping giant. This is another reason why our galaxy is such a peaceful and hospitable place. Our central black hole is not in an active, violent phase. It is a quiet, stable anchor, not a destructive cosmic engine. It rests peacefully at the heart of our calm and orderly galaxy, a silent, sleeping titan at the centre of the great starry city. Let us gently contemplate the most famous feature of a black hole, its boundary, the point of no return. This is known as the event horizon. It is not a physical surface that you could touch. It is simply a threshold in space, an invisible line drawn around the black hole. Once anything, a particle of dust, a beam of light, a wandering star, crosses this line, it can never escape. The gravitational pull becomes so absolute that the fabric of space-time itself is falling into the black hole faster than the speed of light. For our galaxy's supermassive black hole, the event horizon is about 24 million kilometres in diameter. That sounds large, but it is incredibly small for an object of such immense mass. It could fit comfortably inside the orbit of Mercury. Everything we know about physics breaks down inside the event horizon. It is a place where time and space are warped in unimaginable ways. At the very centre, according to our current theories, lies the singularity, a point of infinite density where all the black hole's mass is concentrated. The event horizon is the ultimate cosmic boundary. It is the edge of the known universe. We can study the material swirling around it. We can measure its immense gravity, but we can never know what happens on the other side. It is a place of profound and absolute mystery. It is not a violent edge, but a quiet, final one. It is a silent, one-way door in the universe, a place where the story of matter and energy as we understand it comes to a peaceful, complete, and irreversible end. While our galaxy's core is quiet now, there is fascinating evidence that it may have been much more active in the distant past. In 2010, astronomers using the Fermi Gamma Ray Space Telescope discovered two colossal, mysterious structures extending from the centre of the Milky Way. They are invisible to our eyes and to most telescopes, but they blaze brightly in the highest energy form of light, gamma rays. These structures are two enormous symmetrical bubbles, each one stretching for 25,000 light-years above and below the galactic plane. Together they form a shape like a giant hourglass or a figure eight, centred on our supermassive black hole. They are known as the Fermi bubbles. We do not know for sure what created them, but the leading theory is that they are the ghostly remnants of a huge outburst of energy from our galaxy's centre that happened a few million years ago. This might have been caused by a period when our supermassive black hole was much more active, feeding on a large amount of gas and stars. As it consumed this material, it could have blasted out powerful jets of energy and particles, inflating these gigantic, ghostly balloons of superheated gas. Or it could have been caused by a burst of rapid star formation near the galactic centre, with the combined winds and supernova explosions of thousands of massive stars creating a galactic superwind. Whatever their origin, the Fermi bubbles are a beautiful silent testament to our galaxy's more energetic youth. They are a faint echo, painted in invisible light across the sky, of a time when our sleeping giant was once awake and roaring. Our final stop in the galactic core is to feel out one last invisible force that shapes this extreme environment, the magnetic field. Just as the Earth has a magnetic field that guides our compasses, the galaxy itself has a vast and complex magnetic field, and nowhere is this field stronger or more intricate than at the galactic centre. Recent observations using radio telescopes have revealed a stunning tapestry of magnetic filaments, some of them over 150 light-years long, surrounding Sagittarius A. These filaments are thin, glowing threads of radio energy that trace the magnetic field lines in the region. They look like the strokes of a celestial paintbrush, organised into a beautiful flowing pattern. Some of these magnetic structures are perpendicular to the galactic plane, suggesting they are part of a vast organised field being shaped by the galaxy's rotation and the activity near the black hole. This powerful magnetic field acts like a cosmic traffic controller. It funnels and channels the flow of ionized gas in the galactic centre. It can influence the rate at which the black hole is fed, and it helps to accelerate particles to create cosmic rays. It is an unseen but immensely powerful force that adds another layer of complexity and elegance to the galaxy's heart. It is the quiet, invisible circulatory system of the core, a silent magnetic river flowing around the sleeping giant at the very centre of our cosmic home. Having explored the very heart of our own galaxy, we now pull our focus outward, beyond the edges of the Milky Way's shimmering disk. We will discover that our home is not an isolated island in the cosmic sea. We are part of a small local family of galaxies, bound together by gravity in a slow, silent, and eternal dance. Our first introduction to our cosmic neighbours comes in the form of two beautiful, hazy patches of light, visible to the naked eye from the southern hemisphere. They are not stars, and they are not nebulae within our own galaxy. They are, in fact, two small, irregular galaxies that are our closest and most famous companions. They are the Large Magellanic Cloud and the Small Magellanic Cloud. Named after the explorer Ferdinand Magellan, whose expedition was the first from Europe to record them, these two galaxies are our loyal satellite companions, orbiting the Milky Way much like the Moon orbits the Earth. The Large Magellanic Cloud, or LMC, is about 160,000 light-years away, and is filled with brilliant star clusters and glowing nebulae. It is an active place, with vigorous star formation lighting up its irregular structure. The Small Magellanic Cloud, or SMC, is a little further away, at about 200,000 light-years, and is a smaller, fainter version of its sibling. Together they are like two small companion moons to our vast galactic island. For a long time, we thought they were in a stable, long-term orbit around us. But recent, more precise measurements of their motion suggest they may be first-time visitors to our neighbourhood. They might be on a long, looping path through the cosmos that has only recently brought them close to the Milky Way's immense gravitational pull. Whether they are old friends or new arrivals, their fate is now intertwined with ours. The Milky Way's gravity is pulling on them, shaping them, and as we will see, slowly drawing them in. They are our nearest, brightest, and most beautiful cosmic neighbours. The connection between our galaxy and the Magellanic Clouds is not just gravitational, it is also physical. The immense gravity of the Milky Way is exerting a powerful tidal force on these two smaller galaxies, just as the Moon's gravity creates the tides in Earth's oceans. This gravitational pull is stripping away a vast, invisible river of hydrogen gas from the clouds. This river is known as the Magellanic Stream. It is a colossal arching bridge of gas that stretches across nearly half of the night sky, wrapping around our galaxy. We cannot see it with our eyes, but with radio telescopes that can detect cold hydrogen, it appears as a shimmering, ghostly cosmic thread, connecting us to our neighbours. This stream is a testament to the powerful, silent conversation of gravity taking place over hundreds of thousands of light-years. It is a one-way conversation. The Milky Way is slowly siphoning this gas from its smaller companions. This gas is now flowing towards our galaxy, and over millions of years, it will be incorporated into our own interstellar medium. It will fall like a slow, gentle rain onto our galactic disk, providing fresh fuel for a new generation of star formation. The Magellanic Stream is a beautiful visual reminder that galaxies are not static objects. They interact, they influence each other, and they exchange material. It is a faint, glowing trail that tells a story of a slow, inevitable merger that is happening right now, silently, in the space around us. The Magellanic Clouds are not the only neighbours being influenced by the Milky Way's gravity. In fact, our galaxy is currently in the process of consuming another smaller galaxy. Discovered in 1994, the Sagittarius Dwarf Spheroidal Galaxy is one of our closest satellite galaxies, but it is in the final stages of a galactic merger. Over billions of years, the Milky Way's powerful tidal forces have been stretching and pulling this smaller galaxy apart. It is now a long, disrupted stream of stars, a sort of stellar ghost that is wrapped around the Milky Way, passing through our galaxy's disk multiple times in its orbit. The main, coherent core of the dwarf galaxy is now on the far side of the Milky Way from us, but its stellar stream is all around us. In fact, some of the stars you see in the night sky might not be native to the Milky Way at all, but are former residents of this smaller galaxy that have been captured and adopted by our own. This process is not a violent collision in the way we might imagine. Because the distances between stars are so vast when galaxies merge, the individual stars almost never collide. Instead, it is a slow, graceful dance of gravity, where the two galaxies pass through each other like ghosts. Their stars and dark matter intermingling over hundreds of millions of years. The smaller galaxy's structure is slowly torn apart, and its stars are woven into the fabric of the larger galaxy. The Sagittarius Dwarf Galaxy is a living example of how large galaxies like our own are built, by slowly and patiently cannibalizing their smaller neighbours over the vast course of cosmic time. The ongoing merger with the Sagittarius Dwarf is not a unique event. It is simply the most recent in a long history of similar encounters. When we study the motions and compositions of stars in the Milky Way's vast halo, we find something remarkable. The halo is not a smooth, uniform collection of stars. Instead, it is filled with clumps, streams, and stellar rivers, each moving with a common velocity and direction. These are the ghostly remnants of dozens, perhaps even hundreds, of other small dwarf galaxies that the Milky Way has absorbed over its 13 billion year history. Each stellar stream is like a faint scar, a cosmic fossil, marking the path of a long-dead galaxy that was torn apart and assimilated by our own. The Milky Way is not a single monolithic entity that formed all at once. It is a beautiful, complex mosaic, a composite being that has been assembled piece by piece over eons. It is like a great river that has been fed by countless smaller streams. The streams have now merged with the main body of water, but if you could analyse the currents carefully, you could still detect the faint traces of where each tributary joined. Astronomers, through missions like the Gaia telescope, which maps the motions of 1 billion stars, are now able to trace these ancient currents. They are practicing a kind of galactic archaeology, uncovering the ghosts of these consumed galaxies, and, in doing so, are piecing together the long and gentle history of how our home galaxy was built. Let us now zoom out even further. The Milky Way, with its family of dozens of small satellite galaxies, is not alone. We are part of an even larger gravitationally bound structure known as the Local Group. This is our extended galactic family, our small cosmic county. The Local Group is a collection of over 80 galaxies, all located within a region of space about 10 million light-years in diameter. The vast majority of these galaxies are small dwarf galaxies, like the Magellanic Clouds or the Sagittarius Dwarf. They are faint, unassuming, and tend to cluster around the two largest members of the group. The Local Group is what is known as a binary group, because it is dominated by two great massive spiral galaxies that act as its gravitational anchors. One of these, of course, is our own Milky Way. The other is our slightly larger and more massive neighbour, the Andromeda Galaxy. All the other smaller galaxies in the Local Group are essentially satellites of either the Milky Way or Andromeda. Our little cosmic neighbourhood is a quiet and relatively sparse place. It is not a dense, crowded city of galaxies, but a small, peaceful and gravitationally stable community. We're all bound together by our mutual gravity, slowly orbiting a common centre of mass, like a small, quiet family on a long journey through the even vaster emptiness of intergalactic space. Now, let us turn our attention to the other dominant member of our local group, the queen of our cosmic family. This is the Andromeda Galaxy, also known as Messier 31. It is the closest major galaxy to our own, located about 2.5 million light-years away. On a very dark, clear night, far from city lights, it is just barely visible to the naked eye as a small, faint, fuzzy patch of light. That faint smudge is the most distant object you can see without a telescope. The light you're seeing from it began its journey towards your eyes 2.5 million years ago, long before modern humans existed on Earth. Andromeda is our magnificent big sister. It is slightly larger and more massive than the Milky Way, containing perhaps as many as 1 trillion stars. Through a telescope, it is a breathtaking sight. A perfect glowing spiral tilted at an angle to our line of sight, with a brilliant central bulge and vast sweeping arms of stars and dust. It has its own large family of satellite galaxies just as we do. For a long time, Andromeda was the benchmark against which we measured our own galaxy. It was the beautiful, perfect spiral that we could study from the outside, giving us clues as to what our own Milky Way might look like if we could see it from a distance. It is our cosmic twin, our gravitational partner in the local group. It is the other great anchor of our local universe, and its destiny is profoundly and inextricably linked with our own in a way we are just beginning to understand. For decades, astronomers wondered about the true motion of the Andromeda Galaxy. Was it moving away from us, like most distant galaxies are, as part of the expansion of the universe? Or was it moving closer? The local group is gravitationally bound, meaning its members are not flying apart from each other. By carefully measuring the slight shift in the colour of Andromeda's light, a phenomenon known as the Doppler effect, astronomers made a startling discovery. Andromeda is not moving away. It is heading directly towards us. The Milky Way and the Andromeda Galaxy are on a collision course. They are hurtling towards each other at a speed of about 110 kilometres per second, or about 400,000 kilometres per hour, and in about 4.5 billion years they are destined to meet. Now, the word collision is incredibly misleading. It brings to mind a violent, destructive crash, but a galactic merger is nothing like that. It is one of the most serene, graceful, and creative events in the entire cosmos. Because the space between the stars is so incredibly vast, when the two galaxies begin to merge, individual stars will almost never collide with each other. They will simply pass by one another like ghosts in the night. The two galaxies will flow through each other, their gravitational fields tangling and intertwining in a slow, majestic dance that will last for hundreds of millions of years. The powerful tidal forces will pull long, beautiful streams of stars and gas out of both galaxies, creating spectacular new shapes in the sky. Eventually, after several passes, the two spiral galaxies will settle down and merge into a single, much larger new galaxy. The two cosmic cities will become one. This future event is not something to be feared. It is a quiet, beautiful, and inevitable part of our galaxy's long life cycle, a cosmic union on the grandest possible scale. While the Milky Way and Andromeda are the two giants of the local group, there is a third significant member of our cosmic family. This is the Triangulum Galaxy, also known as Messier 33. It is the third largest galaxy in the local group, though it is considerably smaller than both the Milky Way and Andromeda. It is a beautiful, fluffy, spiral galaxy, with less tightly wound arms and a much smaller central bulge. Its most prominent feature is a gigantic, brilliant stellar nursery, one of the largest known in the local universe. The Triangulum Galaxy is located about 3 million light-years away, and its relationship with its two larger neighbours is a subject of gentle debate among astronomers. It appears to be a satellite of the Andromeda Galaxy, orbiting it in a long, slow path. However, its future is tied up in the great merger of the Milky Way and Andromeda. As our two galaxies approach each other, what will happen to Triangulum? Some models suggest that it will eventually be captured by the newly forming combined galaxy, merging with it several billion years after the main event. Other models suggest it might make a close pass but be flung into a new, wider orbit. And some even suggest that there is a small chance it might hit the Milky Way first, before Andromeda arrives. It is the third partner in this slow, cosmic dance, a beautiful, smaller galaxy that will play a key role in the long-term future and evolution of our local group. Having met the members of our local group, let us take a moment to appreciate the space in which our family resides. Our group of galaxies is an island of matter and gravity in a truly immense ocean of emptiness. The space between galaxy groups and clusters is known as the intergalactic void. It is one of the most empty and peaceful places in the entire universe. The distances are almost beyond feeling. While our local group is about 10 million light-years across, the next nearest major galaxy group is nearly 50 million light-years away. This space in between is not perfectly empty. It is filled with a very, very thin hot gas, known as the warm-hot intergalactic medium. It also contains the lonely hypervelocity stars we met earlier, and perhaps a few truly isolated tiny dwarf galaxies. But for the most part, it is a realm of profound silence and darkness. Imagine standing on a small, quiet island at night. You can see the lights of a few other small islands nearby. This is our local group. But beyond that, there is only a vast, dark, and seemingly endless ocean. The light from the next archipelago of islands takes tens of millions of years to cross that ocean to reach you. This is our place in the cosmos. We are a small, gravitationally bound family, drifting together in a quiet corner of this immense cosmic ocean, a peaceful haven of matter and light in the great, dreary, silent void. Our journey of perspective has one final step outwards. Our local group, this quiet family of galaxies, is itself just one small part of a much, much larger structure. Just as stars are grouped into galaxies and galaxies are grouped into clusters, these clusters themselves are not distributed randomly throughout the universe. They are organised into vast filamentary structures and great sprawling collections known as superclusters. Our local group is located on the outskirts of one such structure, the Virgo supercluster. This colossal entity is a flattened collection of dozens of galaxy groups and clusters, stretching for over 100 million light-years across. At its heart, about 54 million light-years away from us, lies the dense and massive Virgo cluster, a teeming metropolis of over 1,000 galaxies. Our local group is like a small, quiet, rural town, and the Virgo cluster is the great, bustling capital city of our cosmic province. And even this is not the end of the story. The Virgo supercluster, in its entirety, is just one lobe of an even larger structure that astronomers have recently mapped and named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a vast network of 100,000 galaxies, all flowing towards a common gravitational point called the Great Attractor. So our final humbling address in the cosmos is this. We live on planet Earth, in the solar system, in the Orion arm of the Milky Way galaxy, which is part of the local group, on the edge of the Virgo supercluster, within the great cosmic web of Laniakea. It is a perspective that fosters a sense of profound connection to the grand, intricate, and beautifully ordered structure of the universe. Let us now gently bring our focus back inside our own Milky Way. We will drift away from the stars themselves and into the quiet, beautiful spaces in between. This is the realm of the interstellar medium, the cosmic canvas upon which the most ethereal and colourful phenomena of our galaxy are painted. It is easy to think of the space between the stars as a perfect vacuum, a realm of absolute nothingness. But this is not true. The interstellar medium, the substance that fills the galactic disk, is a very thin but very important part of our galaxy's ecosystem. On average, the density is about 1 atom per cubic centimetre. For comparison, the air you're breathing has about 30 billion atoms in that same space. So it is an incredibly good vacuum by earthly standards, but it is not empty. This medium, as we have learned, is about 99% gas, mostly hydrogen and helium, and about 1% dust, tiny solid particles of carbon and silicates. But it is not a uniform, homogeneous fog. It is clumpy and structured, with vast regions of cold, dense molecular clouds where stars are born, and enormous, hot, empty bubbles carved out by supernova explosions. It is a dynamic and complex environment, a canvas that is constantly being stirred, compressed, and repainted by the stars that live within it. Think of it like the air in a large, quiet room. At first glance, it seems to be just empty space. But if a sunbeam comes through the window, you suddenly see the thousands of tiny dust motes dancing in the light. The interstellar medium is like this. It is the almost imperceptible air of the galaxy, the substance that fills the voids, and when it is illuminated by the light of nearby stars, its true beautiful nature is revealed. Some of the most beautiful objects in our galaxy are the glowing clouds of gas known as emission nebulae. These are the stellar nurseries, the places of active starbirth, and they shine with a characteristic beautiful reddish-pink hue. The Orion Nebula is the most famous example, a fuzzy patch of light you can see in Orion's sword, which a telescope reveals to be a stunning, colourful cloud. The reason these nebulae glow is because they are being illuminated from within. Buried deep inside these clouds are very young, very hot, massive blue stars. These stars pour out tremendous amounts of high-energy ultraviolet radiation. This radiation travels into the surrounding hydrogen gas cloud and acts like a celestial blacklight. It energizes the hydrogen atoms, stripping their electrons away. As these electrons inevitably recombine with the hydrogen atoms, they release their excess energy by emitting light at very specific colors or wavelengths. The most common color emitted by hydrogen gas in this state is a deep rosy red known as hydrogen alpha. This is what gives emission nebulae their signature color. They are not reflecting the red light of stars. They're glowing with their own light, like a giant cosmic neon sign. So when you see a picture of a beautiful red nebula, you're looking at a cloud of hydrogen gas that is being excited into fluorescence by the intense light of newborn stars at its heart. It is the soft red glow of cosmic creation. Not all nebulae glow with their own light. Some shine for a much simpler and more gentle reason. They are reflecting the light of nearby stars. These are called reflection nebulae, and they have a very different character and colour from the red emission nebulae. They typically shine with a soft, ethereal and beautiful blue light. A wonderful example is the nebula surrounding the Pleiades star cluster, which looks like a faint blue mist clinging to the bright stars. These nebulae are clouds of interstellar dust. The tiny dust particles in the cloud act like microscopic mirrors, scattering the light from nearby stars. However, they do not scatter all colours of light equally. The small dust grains are much more efficient at scattering shorter wavelengths of light, like blue and violet, than they are at scattering longer wavelengths, like red and orange. This is the exact same reason that our own sky is blue. The molecules in Earth's atmosphere scatter the sun's blue light across the sky, while letting the redder light pass through more directly. So, a reflection nebula is like a cosmic fog illuminated by a nearby streetlight. The fog itself isn't generating light, it is just scattering the light that passes through it, and in the process it appears to glow. Because the blue light is scattered so effectively, the nebula takes on that characteristic blue hue. It is a gentle echo of starlight, a quiet, passive beauty that reveals the presence of invisible clouds of dust, painted blue by the light of their stellar neighbours. Perhaps the most serene and subtly beautiful of all nebulae are those that do not glow at all. These are the dark nebulae. When we look towards the rich, dense star fields of the Milky Way, we can sometimes see patches and lanes that are almost completely devoid of stars. For a long time, early astronomers thought these were holes in the heavens, empty tunnels through which we could see into the true blackness of space beyond. But we now know the truth is the exact opposite. These dark patches are not holes, they are objects. They are the densest and coldest clouds of interstellar gas and dust in our galaxy. These clouds are so thick with dust that they completely block the light of the stars that lie behind them. They are like cosmic curtains, drawn across the bright backdrop of the galactic plane. The famous Horsehead Nebula is a perfect example. We see the shape of a horse's head only because it is a dark, dense cloud silhouetted against a brighter red emission nebula behind it. Another famous example is the Coalsack Nebula, a large dark patch visible near the Southern Cross, which to the indigenous peoples of Australia forms the head of the emu in the sky. These dark nebulae are not just beautiful cosmic shadows, they are also the very earliest stage of star formation. These are the cold, quiet, undisturbed reservoirs of material from which future stellar nurseries will form. Inside their dark, cold hearts, the process of gravitational collapse is just beginning, in a slow, patient process that will take millions of years to eventually ignite new stars. So when you look at a dark nebula, you are seeing the quietest, most peaceful, and most pregnant places in the entire galaxy. They are the silent dark wombs of the cosmos, holding the potential for future light within their deep, cool shadows. There is one more type of nebula we must visit, one that is not about birth, but about a peaceful and beautiful death. These are the planetary nebulae. The name is another historical mistake. They have absolutely nothing to do with planets. They were given this name by early astronomers because their small, round, greenish shapes in early telescopes looked a bit like planets such as Uranus. What they truly are is the final, beautiful act of a dying sun-like star. As we learned earlier, when a star like our Sun runs out of fuel, it swells into a red giant. In the final stages of this phase, the star becomes unstable and begins to gently puff its outer layers of gas away into space. This expanding shell of gas moves outwards from the hot, newly exposed core of the star, the white dwarf. The intense ultraviolet light from this hot core then illuminates the expanding shell of gas, causing it to fluoresce, just like an emission nebula. The results are some of the most intricate, complex, and stunningly beautiful objects in the entire galaxy. They come in all shapes and sizes, perfect rings, like the Ring Nebula, hourglass shapes, like the engraved Hourglass Nebula, or even shapes that look like a cat's eye. These complex shapes are sculpted by the star's rotation, its magnetic fields, and its interactions with any companion stars. A planetary nebula is a very fleeting phenomenon, lasting only about 20,000 years before the gas disperses into the interstellar medium and the central white dwarf cools and fades. It is a star's final, gentle and beautiful exhalation, a brief shining monument to a long life, which enriches the galaxy with its substance before fading quietly into the night. Let us now explore a more whimsical and surprising aspect of the space between the stars. While space itself is a near-perfect vacuum where the concept of smell doesn't really apply, the vast molecular clouds we've been exploring are filled with a surprising variety of complex chemicals, and some of these chemicals, if you could somehow bring a sample of them into a room and smell it, would have very distinct aromas. For example, astronomers have detected vast clouds of ethyl alcohol, the same type of alcohol found in beer and wine near the centre of our galaxy. They have also found ethyl formate, the chemical that gives raspberries their characteristic smell and has a hint of rum. So, in a sense, the centre of our galaxy may smell faintly like raspberries and rum. The interstellar medium is a surprisingly rich chemical factory. The surfaces of coal dust grains provide a perfect sheltered place for simple atoms to link up and form more complex molecules. Scientists have found over 200 different types of molecules in space, including simple sugars, the building blocks of proteins, and even carbon structures like buckyballs. These complex organic molecules, formed in the cold darkness between the stars, may have played a crucial role in the origin of life on Earth, by being delivered to our young planet by comets and asteroids. This adds a wonderfully tangible and grounding layer to our journey. The vast ethereal clouds of the cosmos are not just filled with abstract gases, but with the familiar chemical notes of fruits, spirits, and the very building blocks of life itself. Our exploration of the interstellar medium concludes with something completely invisible but constantly present, a silent, steady rain of high-energy particles known as cosmic rays. Space is not just filled with matter and light, it is also filled with energy in the form of these tiny, fast-moving particles. Cosmic rays are not actually rays in the sense of light. They are atomic nuclei, mostly protons, hydrogen nuclei, and some helium nuclei, that have been stripped of their electrons and accelerated to almost the speed of light. They come from all directions, constantly bombarding our planet and passing through our bodies. Where do they come from? The majority of them, the ones with lower energies, are thought to be accelerated in the shock waves of supernova explosions. The expanding remnant of a supernova acts like a giant cosmic particle accelerator, taking ordinary particles and boosting them to incredible energies. The origin of the most energetic cosmic rays, however, is still a mystery. They may come from the hearts of active galaxies or other exotic, powerful events far beyond our own Milky Way. As these cosmic rays travel through our galaxy, they are guided and deflected by the galaxy's magnetic field, causing them to rain down on us from all directions. They are a constant, invisible, energetic presence, a silent hum that fills the entire volume of our galaxy. They are a reminder that even in the quietest, most empty-seeming parts of space, there is a constant flow of unseen energy, a silent, steady current that connects the most violent events in the cosmos to the quiet space all around us. We have explored the galaxy's places and its inhabitants. Now, let us view the Milky Way as a single living entity, a vast, self-sustaining ecosystem. We will see how stars, gas and gravity all interact in a beautiful closed-loop system that allows the galaxy to live and breathe over billions of years. A healthy ecosystem is one where nothing is wasted, where the end of one life cycle provides the raw materials for the next. Our Milky Way galaxy operates on this exact principle, running the most efficient and long-lasting recycling program imaginable. It is a beautiful galaxy-wide cycle of birth, life, death, and rebirth. The cycle begins in the cold, dense clouds of interstellar gas and dust. Gravity pulls this raw material together to form new stars and planetary systems. These stars then spend millions or billions of years living their lives, acting as cosmic nuclear furnaces. Inside their cores, they fuse light elements into heavier ones. Sun-like stars create elements up to carbon and oxygen. The most massive stars create heavier elements all the way up to iron. When these stars reach the end of their lives, they do not simply vanish. They return their newly forged material back into the galaxy. The sun-like star gently puffs its outer layers away as a planetary nebula, enriching the interstellar medium with carbon and oxygen. A massive star explodes as a supernova, violently scattering all its elements, including the gold, silver and uranium forged in the explosion itself, out into the surrounding space. This enriched material, this stardust, then mixes with the primordial hydrogen and helium clouds. The next generation of stars that forms from these clouds will have a slightly higher concentration of these heavy elements. This is why older stars have fewer metals than younger stars like our Sun. Our own solar system formed from such an enriched cloud about 4.6 billion years ago. The very planet we are on and the bodies we inhabit are made from the recycled remains of countless stars that lived and died long ago. It is a perfect, unbroken circle, a gentle, cosmic system where every ending is just the beginning of a new story. This recycling process is not confined to the flat disk of the galaxy. It involves a beautiful, large-scale circulation system that connects the disk to the halo above and below it. This is known as the galactic fountain model. When multiple massive stars in a star cluster explode as supernovae over a few million years, their combined energy can create a colossal bubble of superheated gas. This bubble is so hot and buoyant that it can break out of the galactic disk entirely, rising up into the galactic halo. This is the fountain part of the model. This hot, enriched gas from the supernovae rises tens of thousands of light years into the halo, like steam rising from a pot. As it rises into the sparse, quiet environment of the halo, it begins to cool down over millions of years. As it cools, it becomes denser and is no longer buoyant. Gravity then begins to pull it back down. The cooled gas then falls like a slow, gentle, cosmic rain back down onto the galactic disk, often hundreds or thousands of light years away from where it started. This falling gas then mixes with the disk material, providing fresh, enriched fuel for the next wave of star formation. This galactic fountain is a slow, majestic, and beautiful process. It is the galaxy's water cycle, a way of circulating and distributing the vital life-giving elements forged in stars, ensuring that all parts of the galactic disk have the chance to share in the recycled stellar harvest. We often picture the galactic disk as a perfectly flat spinning record, but in reality, it has a much more fluid and dynamic character. When we look at the outer edges of the Milky Way's disk, we find that it is not perfectly flat at all. It has a gentle, large-scale warp or wobble. One side of the disk is bent slightly upwards, while the opposite side is bent slightly downwards. Imagine a spinning pizza dough that has been tossed slightly off-centre. It has a gentle rippling warp in its structure. Our galaxy's disk has a similar quality. This warp is not a small feature. It is a significant galaxy-wide distortion. What could cause such a thing? The most likely culprit is gravity. The Milky Way is constantly interacting gravitationally with its satellite galaxies, especially the large and small Magellanic Clouds. As these companion galaxies orbit us, Their gravity gently but persistently tugs on the outer parts of our galactic disk, pulling it slightly out of alignment. The ongoing merger with the Sagittarius dwarf galaxy is also likely contributing to this wobble. These gravitational nudges create a slow rippling effect that propagates through the disk, much like the ripples on the surface of a pond. This gentle, galactic wobble is a beautiful reminder that our galaxy is not an isolated, rigid object. It is a fluid dynamic system, constantly responding to the presence of its neighbours, its structure shaped and moulded by the silent, ever-present conversation of gravity. Orbiting high above and below the galactic disk, drifting through the quiet, dark expanse of the halo, are some of the oldest and most beautiful objects in our galaxy, the globular clusters. These are magnificent ancient cities of stars. Each globular cluster is a tightly packed, perfectly spherical collection of hundreds of thousands, or even millions, of very old stars, all bound together by their mutual gravity. There are about 150 known globular clusters associated with the Milky Way, and they are true relics of the galaxy's formation. All the stars within a single globular cluster were born at the same time from the same primordial cloud of gas over 12 billion years ago. This makes them invaluable cosmic laboratories. By studying the stars in a globular cluster, astronomers can get a perfect snapshot of what a very old stellar population looks like, allowing them to test and refine their theories of how stars evolve. The density of stars at the heart of a globular cluster is immense. The night sky from a planet in such a place would be an overwhelming spectacle, with thousands of ancient reddish stars shining with a steady, brilliant light. Unlike the stars in the disk, which orbit the galactic centre in an orderly flattened rotation, globular clusters have highly elliptical, almost random orbits that take them far out into the halo and then plunging back down through the galactic disk. They are like ancient, orbiting fossils, serene, self-contained cities of elders that have witnessed almost the entire history of the Milky Way, slowly and silently circling the modern bustling metropolis of the galactic disk below. In stark contrast to the ancient, dense and distant globular clusters, we find a very different type of star cluster within the youthful, flat plane of the galactic disk. These are the open clusters. Where globular clusters are ancient cities, open clusters are more like small young towns or cosy neighbourhoods. They are much smaller, containing only a few dozen to a few thousand stars, and these stars are much, much younger. An open cluster is a group of stellar siblings. They're all born at the same time from the same giant molecular cloud, one of the stellar nurseries we visited earlier. After the stars ignite and their stellar winds blow away the leftover gas, the newborn stars remain loosely bound together by their mutual gravity. The Pleiades, or Seven Sisters, is the most famous example of a young open cluster, easily visible to the naked eye as a tiny misty dipper. Unlike globular clusters, open clusters are not tightly bound enough to survive forever. Over tens or hundreds of millions of years, as the cluster orbits within the galactic disk, two things happen. First, gentle gravitational tugs from passing gas clouds and other stars slowly pull the cluster apart. Second, the stars themselves gradually drift away from each other. An open cluster is like a family of children that grows up and eventually moves out to live their own lives in the wider city. Our own sun was almost certainly born in an open cluster like the Pleiades, but its stellar siblings have long since drifted away and are now scattered across our part of the galaxy. Just as a planet has a habitable zone around its star where the temperature is right for liquid water, our galaxy may have a similar zone where the conditions are just right for the development of complex life. This is a gentle, theoretical concept known as the galactic habitable zone. It is a specific region of the galactic disk that is a Goldilocks zone. Not too hot, not too cold, but just right. If you are too close to the galactic centre, the environment is too dangerous. The star density is very high, increasing the risk of a nearby star passing close enough to disrupt planetary orbits. More importantly, the levels of high-energy radiation from the central black hole and from frequent supernova explosions are likely too intense for life to survive. The cosmic downtown core is just too chaotic. If you're too far out in the galactic suburbs, on the other hand, the environment might be too impoverished. The concentration of heavy elements, or metals, is much lower in the outer regions of the galaxy. These heavy elements are crucial for forming rocky planets like Earth in the first place. Without enough of this recycled stardust, you might only get gas giants. The galactic habitable zone is the broad, quiet middle ring of the galaxy where these two factors are perfectly balanced. It is a region where there are enough heavy elements to build terrestrial worlds, but not so much stellar crowding and radiation that life would be constantly threatened. Our own solar system is located comfortably within this proposed zone, which might be one of the key reasons why life was able to flourish here, in our quiet, stable, and well-provisioned cosmic neighbourhood. Space, of course, is a near-perfect vacuum, and without a medium for sound waves to travel through, it is profoundly silent. The universe does not have a literal voice, but we can, in a metaphorical and beautiful way, listen to our galaxy. Astronomers do this through a process called data sonification. They take data from telescopes, data that comes in the form of light at different frequencies, like radio waves, infrared, or X-rays, and they translate that data into audible sound. Imagine assigning a different musical note to different elements, like hydrogen and helium, or a different instrument to different structures, like stars and gas clouds. By scanning an image of a galaxy and translating its light and colours into sound, we can create a sort of cosmic symphony. The dense, bright core of the galaxy might become a deep, steady hum. The wispy, star-forming regions in the spiral arms could be translated into higher, more delicate notes like wind chimes. The passage of a supernova remnant could be a gentle crescendo and then a soft fade. This is not what the galaxy sounds like, but it is a way for our human senses to perceive the vast amounts of data in a more intuitive and emotional way. It allows us to experience the structure, density, and composition of our galaxy, not just with our eyes, but with our ears. It is a beautiful marriage of science and art, a way to listen to the silent, harmonious patterns that exist in the grand, silent music of the cosmos. We have felt the pull of the galaxy's gravity, and we have bathed in the light of its stars. But there is another vast, invisible force that permeates the entire galactic ecosystem, its magnetic field. Like a gossamer-thin, invisible web, the Milky Way's magnetic field stretches across its entire 100,000 light-year expanse, shaping the interstellar medium and guiding the flow of charged particles. This magnetic field is generated by a process called a dynamo, which is similar to how the Earth generates its own magnetic field. The rotation of the galaxy, combined with the churning, turbulent motions of the ionized gas within the disk, acts like a giant electric generator, creating and sustaining a large-scale magnetic field. The field generally follows the spiral structure of the arms, like magnetic highways running along the stellar avenues. This field, though thousands of times weaker than the magnetic field at the Earth's surface, plays a crucial role in the galaxy's life. It helps to shape the interstellar clouds, sometimes providing a gentle pressure that resists gravitational collapse, and other times channeling the gas into denser regions to help trigger star formation. It is also the invisible lattice upon which high-energy cosmic rays travel, guiding these tiny particles on their long journeys across the galaxy. This magnetic field is the galaxy's quiet, unseen nervous system, a silent, pervasive force that helps to organize and structure the beautiful chaos of the galactic disk, adding one more layer of invisible elegance to the cosmic ecosystem. We end our exploration of the galactic ecosystem by demystifying one of its most beautiful features, the spiral arms. It is tempting to think of them as solid structures, like the arms of a spinning pinwheel, with stars physically attached to them. If this were true, the arms would wind themselves up so tightly after a few rotations that the spiral pattern would disappear. The fact that we see beautiful, open spirals in so many galaxies tells us something else must be going on. The leading theory is that the spiral arms are not a physical structure, but a pattern that moves through the disk. They are density waves. Imagine a stretch of highway with a slow-moving truck on it. The truck is causing a traffic jam. The jam itself, the dense region of cars, moves slowly down the highway. But the individual cars are not stuck in it forever. They drive up to the jam, slow down for a while, and then accelerate out the other side. The spiral arms are cosmic traffic jams. They are regions of slightly higher density that are sweeping slowly through the galactic disk. Stars, gas, and dust in their regular orbits encounter these density waves, are compressed as they pass through, and then move on. It is this act of compression, especially of the gas clouds, that triggers the bursts of new star formation. This is why the spiral arms are so bright and blue. They are being constantly lit up by the brilliant short-lived blue stars that have just been born. The arms are not a place, but an event. They are a beautiful, slow-motion ripple of creation, a gentle, self-sustaining pattern that elegantly organises the process of stellar birth across the entire galactic disk. Let us now allow our journey to drift gently backward in time. The galaxy is not just a place. It is a story that has been unfolding for over 13 billion years. We will now learn how to read the echoes of this deep past, how to see the galaxy's history written in the faint, ancient light of its stars. Before we explore its history, let us contemplate the sheer age of our home. The Milky Way is an ancient city. By studying the ages of the oldest stars within it, particularly those found in the ancient globular clusters, astronomers have determined that our galaxy began to form about 13.6 billion years ago. This is a truly profound age. The universe itself is only slightly older, at about 13.8 billion years. This means that our Milky Way is one of the pioneering galaxies, one of the very first great star systems to begin forming in the entire universe. It began its life not as the grand spiral we see today, but as a series of smaller, clumpy protogalaxies, formless clouds of primordial gas that were just beginning to collapse and ignite their first generation of stars. This was happening just a few 100 million years after the Big Bang, in the dim, early twilight of the cosmos. For over 13 billion years since then, our galaxy has been growing, evolving, and changing. It has been built up through the slow, steady merger of these smaller galaxies, and its substance has been continually recycled through countless generations of stars. This immense age provides a quiet sense of perspective. The entire history of our planet, the rise and fall of the dinosaurs, the slow emergence of humanity, all of these events are just the most recent fleeting moments in the incredibly long and serene life story of our galactic home. We are living in a city that is almost as old as time itself, a place of deep, quiet, and ancient history. The history of the galaxy is not just a theoretical concept. It is written all around us, in the very light that reaches our eyes from the night sky. This is because light, while incredibly fast, does not travel instantaneously. It takes time for light to cross the vast distances of space. This simple fact turns our telescopes into time machines. When we look at a star, we're not seeing it as it is right now. We are seeing it as it was when the light left it. The light from our own sun takes about 8 minutes to reach Earth. The light from our nearest stellar neighbour, Proxima Centauri, takes over 4 years. The light from the bright star Vega takes 25 years. The light from the stars in the Orion Nebula has been travelling for over 1,300 years to reach us tonight. And when we look at the Andromeda Galaxy, we are seeing 2.5 million-year-old light. This means the night sky is not a snapshot of the present moment. It is a beautiful layered tapestry of the past. The further we look, the deeper back in time we see. The starlight arriving at your eyes tonight began its journey at different moments in history. Some of it started this afternoon, some of it started when the Roman Empire was at its height, and some of it started long before humans walked the earth. The entire sky is a vast, cosmic fossil record. By studying the light from different parts of our galaxy, we can piece together its history, seeing echoes of what it was like hundreds, thousands, or even millions of years ago. The universe's story is not locked away. It is being constantly told to us by the gentle, time-travelling messengers of starlight. Let us use our time-travelling vision to imagine the galaxy in its earliest days. After the Big Bang, the universe was filled with only the simplest elements: hydrogen, helium, and a tiny trace of lithium. There were no heavy elements, no carbon, no oxygen, no iron. The very first stars to form in our young galaxy, known as population 3 stars, were born from this pure primordial gas. We have never directly seen one of these stars. They were all incredibly massive and lived very short lives, burning out long, long ago. But our theories tell us what they must have been like. Because they lacked the heavy elements that help to cool modern gas clouds, they could only form from very large, massive clumps of gas. This means the first stars were true giants, hundreds of times more massive than our sun. They would have been incredibly hot and shone with a brilliant blue-white light, millions of times more luminous than our own star. They would have lived for only 1,000,000 years or so before running out of fuel and exploding in titanic supernovae. But in their brief, brilliant lives and spectacular deaths, they performed a task of monumental importance. They were the first cosmic forges. Inside their cores and in their final explosions, they created the first batches of heavy elements and scattered them into the pristine gas of the young galaxy. This act of cosmic seeding was the crucial first step. It was this stardust from the very first generation of stars that allowed the second generation to form, and then the third, each one slightly more enriched than the last. Until finally, billions of years later, there was enough carbon, oxygen, and iron to form rocky planets, and eventually, us. The modern picture of how our galaxy grew is a beautifully gentle and organic one. The Milky Way was not born in a single grand collapse of a giant gas cloud. Instead, it was patiently assembled over billions of years through a process called hierarchical merging. The story begins with very small proto-galaxies, little more than large star clusters or tiny dwarf galaxies, which were the first gravitationally bound systems to form in the early universe. These small systems, numbering in the hundreds, then began to interact and merge. Gravity, the great silent sculptor of the cosmos, slowly drew them together. Over the first few billion years of the universe's history, these smaller building blocks collided and combined, their stars and gas clouds intermingling to form progressively larger and larger galaxies. This was a period of gentle but constant cosmic construction. The Milky Way's halo, with its ancient globular clusters, was likely built up during this early chaotic period of merging. Eventually, the largest of these merging galaxies settled down and formed the main disk of the Milky Way. But the process did not stop. Our galaxy has continued to grow ever since by pulling in and absorbing smaller dwarf galaxies that have wandered too close, a process that continues to this day with the Sagittarius dwarf galaxy. So, our home galaxy is not a single pristine creation. It is a beautiful composite quilt stitched together from the fabric of countless smaller galaxies that lived and died long ago. Its structure holds the memory of all the cosmic streams that have fed it, creating the vast, swirling river of stars we inhabit today. This understanding gives our galaxy a sense of deep, layered history, a story of slow, patient, and gentle assembly over the entire age of the universe. How do we know so much about the galaxy's assembly and the ghosts of its past? A huge part of the answer lies with a remarkable space observatory called Gaia. Launched by the European Space Agency in 2013, Gaia is on a mission to create the most precise and comprehensive three-dimensional map of our galaxy ever made. Its task is one of incredible patience and precision. For years, it has been slowly scanning the entire sky, over and over again, measuring the exact position, distance, motion, and brightness of over 1 billion stars. This is a feat of cosmic cartography on an unprecedented scale. By knowing the precise motion of so many stars, both their speed and their direction, astronomers can essentially rewind the clock. They can trace the paths of these stars backwards in time to see where they came from. This is how they are able to identify the great stellar streams and moving groups that are the remnants of consumed dwarf galaxies. Gaia's data allows us to see the galactic fossil record with stunning clarity. Imagine trying to understand the history of a great city just by looking at a single photograph of it. Now, imagine you were given a video showing the precise movements of every single resident over the last 50 years. That is the difference Gaia is making. It is revealing the hidden currents and flows within our galaxy, showing us which stars are moving together, which were born together, and which have come from somewhere else entirely. It is a quiet, patient, and revolutionary mission that is gently uncovering the secret history of our Milky Way, one star at a time. Gaia's precise measurements have also confirmed a subtle and fascinating feature of our galaxy's structure. The main disk is actually made of two distinct components. There is a thin disk and a thick disk. The thin disk is the region we've been most familiar with. It is about 1,000 light-years thick and contains our Sun, most of the galaxy's gas and dust, and almost all of the young newborn stars. It is the site of all the current star formation. Enveloping this is the thick disk, a puffier, more vertically extended structure, perhaps 3,000 to 5,000 light-years thick. The stars in the thick disk are, on average, much older than the stars in the thin disk. They're also moving up and down more rapidly, giving the disk its greater height. This two-part structure is a quiet, fossilised clue about a dramatic event in our galaxy's distant past. The leading theory is that the thick disk is the original disk of our galaxy, formed early in its history. Then, about 8 to 10 billion years ago, a fairly large dwarf galaxy, perhaps the size of the small Magellanic Cloud, collided with and was absorbed by the Milky Way. This merger was so significant that it heated and puffed up the existing disk, scattering its stars into wider, more inclined orbits, thus creating the thick disk. After the dust settled, the remaining gas fell back into a new, thinner plane, and this is where all subsequent star formation has taken place, creating the thin disk we live in today. This layered structure is a silent monument to one of the most significant mergers in our galaxy's long construction history. In our journey through the galaxy's past, we can even meet a specific individual resident that serves as a direct link to the dawn of time. This is the star HD 140283, unofficially and affectionately nicknamed the Methuselah star. It is located relatively nearby, only about 200 light-years from Earth, and it is one of the oldest known stars in the entire universe. The Methuselah star is a subgiant star that is extremely metal-poor, meaning it is made almost entirely of hydrogen and helium, a sure sign of great age. For a time, its estimated age was actually calculated to be older than the universe itself, which was a baffling paradox. However, with more refined measurements of its distance and composition, its age has been revised to be about 13.5 billion years old, making it just slightly younger than the universe, but still ancient. This single star, which you could see with a simple pair of binoculars, was born when our galaxy was in its absolute infancy. It was shining long before the galactic disk had fully formed. It has been a silent witness to almost the entire story we have been exploring. It saw the great mergers that built our galaxy. It has orbited the core hundreds of times, and it has seen countless generations of other, more massive stars be born and die. It is a true time capsule, a single, tangible point of light that connects our modern neighbourhood directly to the dim, mysterious twilight of cosmic dawn. The history of the Milky Way is not just one of direct mergers, it is also shaped by close calls and near misses. The gravitational dance with our satellite galaxies, like the Magellanic Clouds, has had profound effects on our galaxy's evolution, even without a direct collision. Each time a satellite galaxy makes a close pass, its gravity sends gentle but powerful ripples through our galaxy's disk. These gravitational disturbances can compress the interstellar gas clouds, triggering enormous galaxy-wide bursts of star formation. The gentle warp in our galactic disk is a present-day example of such a gravitational interaction. By studying the ages of star clusters, astronomers can identify periods in the past when our galaxy experienced a sudden, dramatic increase in its rate of star birth. These periods often coincide with the calculated times of close passages of satellite galaxies, like the Sagittarius Dwarf or the Magellanic Clouds. It is like striking a bell. The close pass of a smaller galaxy is the strike, and the resulting wave of star formation is the ring that echoes through the disk for hundreds of millions of years. Our galaxy's history is not a steady, constant process. It is a story punctuated by these periods of gentle disturbance and subsequent renewal. The silent, gravitational whispers of our nearest neighbours have been instrumental in stirring the cosmic pot, ensuring that our galaxy remains a dynamic, vibrant and creative place. These near misses are a crucial and gentle part of the long, slow and ever-evolving dance of our local group. Our journey has taken us through the vast spaces, diverse populations and deep history of our galaxy. Now, in this quiet, reflective part of our exploration, we turn to one of the most profound and gentle questions of all. In this city of 400 billion suns, are we the only ones looking up and wondering? Let us now explore the quiet search for other worlds and the possibility of other stories unfolding in the starlight. For thousands of years, we knew of only a handful of planets, the ones in our own solar system. They seem like special, rare jewels in the vast emptiness. But one of the most breathtaking discoveries of the last few decades has been the realization that this is not the case at all. Planets are not rare, they're incredibly, wonderfully common. In fact, they are the normal expected outcome of star formation. Based on the thousands of planets we have now discovered orbiting other stars, astronomers have been able to make a stunning statistical projection. There are more planets in our galaxy than there are stars. The current estimate is that, on average, every star in the Milky Way hosts at least one planet. This means our galaxy is home to not just 400 billion suns, but perhaps 1 trillion or more worlds. Suddenly the galaxy is transformed in our imagination. It is no longer just a city of stars, it is a city of 1 trillion solar systems. The night sky is not just a collection of distant suns, it is a canopy of countless potential worlds, each one orbiting its own star, with its own unique geography, its own alien sky, its own quiet story. This discovery changes everything. The question is no longer, are there other planets out there? The question is now, with so many worlds to choose from, which ones might be like our own? The silent, empty spaces have been filled with an almost infinite sense of possibility. How did we go from knowing of only our own planets to knowing of thousands? A huge part of the credit goes to a single, remarkably patient space telescope, NASA's Kepler mission. Launched in 2009, Kepler was designed to answer one simple question: how common are Earth-like planets in our galaxy? To do this, it employed a beautifully simple and elegant method known as the transit method. Kepler spent 4 years staring without blinking at a single, small patch of the sky in the constellation Cygnus. This patch of sky contained about 150,000 stars. Kepler's mission was to measure the brightness of each of these stars with incredible precision over and over again. It was looking for a tiny rhythmic dip in a star's light, the kind of dip that could only be caused by a planet passing in front of the star from our point of view, creating a miniature eclipse. It was an act of incredible cosmic patience, like watching thousands of candles from miles away, hoping to see one of them flicker for just a moment as a moth passes in front of it. And it worked. Kepler's patient vigil was a spectacular success. It discovered thousands of confirmed exoplanets and thousands more candidates. It single-handedly changed our understanding of our place in the galaxy, revealing that planets of all sizes are incredibly common. Kepler was a quiet, robotic pioneer that opened our eyes to the breathtaking reality that the galaxy is teeming with worlds, transforming the search for other Earths from a distant dream into a real, tangible and ongoing exploration. The thousands of planets discovered by Kepler and other missions have revealed a stunning and sometimes bizarre planetary zoo, filled with types of worlds that we never imagined because they do not exist in our own solar system. This has wonderfully expanded our concept of what a planet can be. Among the most common types of planets Kepler found are worlds known as super-Earths and mini-Neptunes. These are planets with sizes somewhere between that of Earth and Neptune. Our solar system has nothing in this size range. We have small rocky planets and then enormous gas giants, with nothing in between. Yet this appears to be the most common size of planet in the entire galaxy. Are they large rocky worlds with thick atmospheres, or are they small, gassy worlds with a solid core? We're only just beginning to find out. Kepler also found many hot Jupiters. These are gas giant planets, like Jupiter, but they orbit incredibly close to their parent stars, often completing a full year in just a few Earth days. Their proximity to their star makes their atmospheres superheated to thousands of degrees. We also have found rogue planets, worlds that do not orbit a star at all but wander, cold and dark, through the interstellar void, having been ejected from their home systems long ago. This incredible diversity is a gentle reminder that our own solar system, with its orderly progression from small rocky worlds to distant gas giants, may be just one possible outcome of planet formation among countless others. The galaxy is a grand laboratory, and it has created a far richer and more imaginative variety of worlds than we ever thought possible. Amidst this incredible diversity of worlds, the quiet, ultimate goal for many astronomers is the search for a true Earth twin, a planet that is about the same size and mass as Earth, made of rock and orbiting a sun-like star at just the right distance for liquid water to exist on its surface. This perfect distance is known as the star's habitable zone, or the Goldilocks zone. This is the quiet, ongoing quest for a pale blue dot orbiting another sun. Finding such a world is incredibly difficult. A small rocky planet passing in front of its star creates a dip in light that is almost imperceptibly small, like trying to detect a flea crawling across a car's headlight from 100 miles away. And yet, we are succeeding. We have found a growing number of potentially habitable Earth-sized worlds. Kepler-1a Ceph was the first Earth-sized planet found in its star's habitable zone. The TRAPPIST-1 system has 7 rocky, Earth-sized planets, 3 of which are in the habitable zone of their small, cool red dwarf star. Proxima Centauri b is a potentially rocky planet, orbiting our very nearest stellar neighbour, right in its habitable zone. We do not yet know if these worlds have atmospheres, if they have water, or if they are truly habitable. Answering those questions is the great challenge for the next generation of telescopes, like the James Webb Space Telescope, which can analyse the starlight that passes through a planet's atmosphere to look for the chemical signatures of water, oxygen, or methane. This search is a profound and humbling one. It is not just a search for rocks and water, it is a search for a reflection of ourselves in the cosmic ocean. It is the quiet, hopeful search for a world where another story, perhaps even a story like our own, might have had the chance to unfold. As we search for Earth's twin, we may discover that the most common type of habitable world in the galaxy is very different from our own. Our planet is a beautiful balance of land and sea, but it is possible that many potentially habitable planets are water worlds, planets that are completely covered by a single, global ocean thousands of kilometres deep. A planet that forms with a slightly higher percentage of water than Earth could easily end up in this state. With no continents to break the waves, the surface of such a world might be a place of unimaginable storms and colossal tides. But deep beneath the turbulent surface, in the crushing pressures and quiet darkness of the deep ocean, the conditions could be very stable. On Earth, life may have actually begun near hydrothermal vents on the ocean floor. A global ocean on an exoplanet could provide a wonderfully stable and protected environment for life to emerge and thrive, completely independent of the weather on the surface. Imagining such a world is a wonderfully serene and peaceful exercise, a planet of endless, calm, deep water, its surface perhaps covered in a thick layer of ice, with a hidden liquid ocean beneath. A world without shores, without boundaries, just a single, unified body of water under the light of an alien sun. It is a gentle reminder that a habitable world may not look anything like our own, and that the galaxy may have found many different and beautiful ways to create a cradle for life. One of the most surprising and resilient discoveries in the search for other worlds is that planets can exist in the most unlikely of places, even orbiting the corpses of dead stars. The very first exoplanets ever confirmed were discovered in 1992, not around a normal sun-like star but around a pulsar. A pulsar is a rapidly spinning neutron star, the hyperdense remnant of a massive star that has gone supernova. It is a place bathed in intense radiation, the last place you would expect to find a stable planetary system. And yet, there they were. At least 3 small rocky worlds orbiting this stellar ghost. How did they get there? They are likely not the original planets of the star. Any original planets would have been destroyed in the supernova explosion. Instead, these are thought to be second-generation planets. They formed from the dusty debris that was left over from the supernova, a disk of material that slowly coalesced into new worlds around the dead star's remnant. We have also found evidence of planets and planetary systems orbiting white dwarfs, the cooling embers of sun-like stars. This speaks to the incredible tenacity of planet formation. It is a process that can happen even in the most extreme and inhospitable environments, a cosmic impulse to create worlds out of dust and debris. It offers a strange and quiet hope. Even after a star has died, even after its violent end, new worlds can be born from its ashes, continuing the cosmic story in the long, quiet twilight. Beyond the search for habitable worlds, there is another, even more profound search. It is a search not just for life, but for intelligence. This is the search for extraterrestrial intelligence, or SETI. It is one of the most passive and peaceful explorations we have ever undertaken. It is, quite simply, the act of listening. Using large radio telescopes, SETI astronomers scan the skies, listening for a very specific type of signal, a signal that is narrow-band, repetitive, and clearly artificial, a signal that could not be produced by any known natural cosmic phenomenon. They are listening for a whisper of technology in the great cosmic static. This search is predicated on a simple, hopeful assumption that if another technological civilization exists, they, like us, may have discovered radio waves as a means of communication. And if they are broadcasting signals either intentionally to make contact or unintentionally as part of their own civilization's communications, some of that signal might be travelling through space, waiting to be detected. So far, we have found only silence. The universe, it seems, is very quiet, but the search is a testament to our own enduring curiosity and hope. It is a profoundly optimistic act. To point a telescope at a distant star and listen for a sign of kinship is to believe in the possibility of connection across the vast, silent gulfs of space and time. It is not a frantic search, but a patient, quiet, and hopeful vigil, a way of saying to the universe, "We are here, is anyone else?" This great cosmic silence leads us to one of the most famous and gentle paradoxes in all of science. It is called the Fermi paradox, named after the physicist Enrico Fermi, who is said to have first posed the question during a lunch conversation. The paradox is simple and profound. It goes like this. Our galaxy is incredibly old and incredibly vast. It contains hundreds of billions of stars and likely 1 trillion or more planets. Statistically, it seems almost inevitable that life, and even intelligent technological life, should have arisen many times over the galaxy's long history. Some of these civilizations could be millions or even billions of years older than our own. If even one of them had developed the technology for interstellar travel, even at very slow speeds they would have had more than enough time to explore and colonize the entire galaxy by now. And yet, when we look up at the sky, we see no evidence of them. We find no giant alien structures, we detect no interstellar communications, we see no signs of galactic engineering. The universe, as far as we can tell, is empty and silent. So, the question is simple. Where is everybody? This is the Fermi paradox. It is the jarring contradiction between the high probability of extraterrestrial intelligence and the complete lack of any evidence for it. The Fermi paradox is not a problem that needs to be solved, but a quiet mystery to be contemplated. And there are many gentle, non-alarming potential solutions to this great silence. Perhaps the paradox is not a paradox at all. One possibility is that life itself is common, but intelligent. Technological life is incredibly rare. The step from a single living cell to a civilization that builds radio telescopes might be the greatest filter of all, a step so improbable that it has happened only once, here on Earth. Or perhaps intelligent civilizations do arise, but they are very short-lived. They might discover technology and then quickly destroy themselves through war or environmental collapse, long before they ever venture to the stars. A more peaceful solution is simply that the distances are too vast. Interstellar travel might be so difficult and so resource-intensive that no civilization ever truly bothers with it. Or maybe they are out there, but they are not broadcasting in a way we can detect. Perhaps they use technologies we cannot even imagine, like neutrinos or gravitational waves, to communicate. Or maybe, in a very humbling thought, they are aware of us but have chosen not to interfere, treating our world like a cosmic wildlife preserve. The silence of the universe does not have to be a lonely one. It could be a silence born of immensity, of rarity, or even of respect. The mystery remains a gentle, open question. And so, we end this chapter of our journey by simply returning to the quiet wonder of the night sky. The search for company, for other worlds and other minds, has not yet given us any definitive answers. It has only given us a deeper appreciation for the boundless potential that surrounds us. We now know that every single point of light you see in the sky is a sun, and we now know that almost every one of those suns has a family of planets. We may not know what those planets are like, or what stories are unfolding upon them. But the possibility is now real. The galaxy is no longer a collection of lonely stars, but a forest of 1 trillion worlds. That star over there could be orbited by a planet of endless oceans. That one could be home to a world of giant windswept deserts. And that one, just perhaps, could be home to something we have only ever dreamed of. Another conscious being, looking up at their own sky and wondering, just as we are, if they are alone. The silence of the galaxy is not empty. It is filled with the quiet, gentle and peaceful weight of infinite possibility. and that, in itself, is a truly beautiful thing. Our journey is now drawing to its final stages. We have looked around us and deep into the past. Now, let us cast our gentle gaze forward into the deep, deep future. We will not look for frantic predictions, but for the slow, graceful, and inevitable changes that await our home galaxy over the grand arc of cosmic time. The Milky Way we see today, with its brilliant spiral arms lit up by the birth of new stars, is a galaxy in its vibrant prime. But this youthful vigour cannot last forever. The process of star formation requires a constant supply of cold, dense gas. And the galaxy's supply of this gas is finite. Every time a new star is born, some of the galaxy's creative potential is locked away. While stars do recycle their material back into the galaxy when they die, the process is not 100% efficient. Some mass is always locked up in the long-lived red dwarfs and in the stellar remnants like white dwarfs and neutron stars. Slowly, almost imperceptibly, the galaxy is using up its reservoir of fuel. The rate of star formation in the Milky Way has been slowly declining for billions of years, and this trend will continue. In the far, far future, billions of years from now, the great stellar nurseries will begin to run dry. The beautiful emission nebulae will fade. The brilliant blue giant stars will become rarer and rarer. The galaxy will slowly begin to change its colour. As the blue stars die off and are not replaced, the galaxy's overall light will become dominated by the older, longer-lived and redder stars. The Milky Way will slowly transition from a vibrant blue spiral galaxy into a more settled, sedate red galaxy. This is not a death, but a slow, graceful aging. It is the galaxy settling into a long, quiet and peaceful twilight, its most creative and energetic days slowly giving way to a period of ancient, serene maturity. On a more personal timescale, the future of our own home star, the Sun, is also a quiet, inevitable story. Our Sun has been shining steadily for about 4.6 billion years, and it has enough hydrogen fuel in its core to continue shining as it does now, for about another 5 billion years. But eventually that fuel will run out. When this happens, the Sun's core will begin to contract and heat up, and this will cause its outer layers to expand dramatically. The Sun will begin its transformation into a red giant. Over the course of a few 100 million years, it will swell to become over 200 times its current size, its surface becoming cooler and redder. Its expanding outer atmosphere will engulf the orbits of Mercury and Venus, and very likely the Earth as well. After its red giant phase, the Sun will shed its outer layers to form a beautiful planetary nebula, and its core will be left behind as a white dwarf, a cooling, Earth-sized ember that will slowly fade over the eons. This is a distant, far future event, so remote that it is difficult to feel any sense of alarm. It is simply the natural, peaceful and expected end of our star's long life. It is the final chapter in the story of our solar system, a quiet, gentle reminder that even stars are not eternal, and that all things in the cosmos are part of a great, slow and unending cycle of change. At around the same time that our Sun is beginning to end its life, a much grander drama will be unfolding for our galaxy as a whole. As we discovered earlier, the Milky Way and the Andromeda Galaxy are on a collision course, destined to merge in about 4.5 billion years. Let us imagine what this slow, graceful event will be like. As the two galaxies get closer, their shapes will begin to distort under their mutual gravitational pull. Long, beautiful tails and bridges of stars and gas, called tidal tails, will be drawn out from both galaxies, creating a spectacular tangled dance in the sky. When the two galactic disks first pass through each other, the night sky for any observer within them would be a breathtaking sight, filled with the stars and nebulae of another galaxy. Still, the individual stars would not collide. The two great cities would simply interpenetrate, their populations mixing peacefully. The two galaxies will then separate, travel out for a few 100 million years, and then be pulled back together by gravity for a second pass. After 2 or 3 of these passes, their separate cores will finally merge, and they will settle down into a single, much larger new galaxy. The beautiful spiral structures of both the Milky Way and Andromeda will be destroyed in the process. The new combined galaxy will be what is known as a giant elliptical galaxy, a huge, round or football-shaped swarm of older golden-hued stars with very little gas, dust or new star formation. Some astronomers have already given this future galaxy a beautiful nickname, Milky Way. It will be the serene, final product of the long, slow and graceful union of the two largest members of our local group. The merger of the Milky Way and Andromeda will not be an ending. In fact, it will trigger one last, magnificent burst of cosmic creation. As the two galaxies collide and their vast clouds of interstellar gas and dust are compressed and churned together, the conditions will become perfect for a galaxy-wide starburst. The rate of star formation will skyrocket for a few 100 million years. A final, brilliant generation of stars will be born from the combined gas reservoirs of the two galaxies. The newly forming Milky Way galaxy will blaze with the light of millions of newborn blue stars and the glow of countless stellar nurseries. It will be a brief but spectacular period of cosmic renewal, a final, celebratory firework display before the new galaxy settles into its long, quiet retirement. This starburst will use up most of the remaining gas in the new galaxy. So, after this final flurry of activity has faded, and this last generation of massive stars has lived out its short, brilliant life, star formation in Milky Way will largely cease. The galaxy will then begin its slow, gentle fade into red, elliptical maturity. This final burst of creation is a beautiful part of the story, a reminder that even in an event as grand as a galactic merger, the universe's primary impulse is not to destroy, but to create. It is a gentle, speculative exercise to imagine what the night sky would look like during this grand merger. Our own sun will be in its red giant phase by then, so the Earth as we know it will likely be gone. But if we imagine an observer on a resilient planet in the new Milky Way galaxy, what would they see? For millions of years during the merger, the sky would be a scene of breathtaking, slow-motion change. As Andromeda first approaches, it would grow from a faint fuzzy patch into a magnificent sprawling spiral that fills a huge portion of the sky. As the galaxies interpenetrate, the familiar band of the Milky Way would be gone, replaced by a chaotic, beautiful, and much denser tapestry of stars, a mix of residents from both galaxies. The sky would be filled with the bright glowing knots of new star formation triggered by the collision. After the merger is complete and the new elliptical galaxy is settled, the sky would be different again. There would be no Milky Way band at all. The stars would be distributed much more uniformly across the sky. The overall colour of the night would be a soft golden yellow, the light of the trillions of older stars that now make up the galaxy. There would be very few blue stars and very few glowing nebulae. It would be a sky that is more crowded, more uniform and perhaps more ancient and serene. It would be a sky of profound peace, the sky of a galaxy that has finished its long, dynamic life of creation and has settled into a quiet and graceful eternity. Now, let us cast our minds forward into the truly deep, almost unimaginable future, trillions upon trillions of years from now. By this point, the expansion of the universe will have carried all other galaxies so far away that their light will no longer be able to reach us. Our Milky Way galaxy will be an isolated island universe, alone in an endless dark void. All star formation will have long since ceased. All the sun-like stars will have burned out, leaving behind cold, dark white dwarfs. The massive stars will be long gone, having become neutron stars and black holes. What will be left? What light will still shine in this impossibly distant future? The only light will be the faint, gentle, reddish glow of the most common and longest-lived stars in the universe, the red dwarfs. For trillions of years, an almost incomprehensible span of time, these small, slow-burning stars will be the only beacons in the cosmos. The universe will enter what is sometimes called the stelliferous era's final phase, the age of red dwarfs. The universe will be a much dimmer, quieter and colder place, illuminated only by the faint ember-like glow of these incredibly long-lived stars. It is a vision of ultimate cosmic peace, a universe that has slowed to an almost complete stop, basking in the faint, serene and seemingly eternal twilight of its final, most steadfast inhabitants. But even the red dwarfs cannot shine forever. After trillions of years, even they will finally exhaust their immense supply of hydrogen fuel. They do not swell into red giants. They will simply, quietly and gently fade away, becoming small, dark white dwarfs themselves. And when the last red dwarf star finally flickers and dies, the age of stars will be over. the universe will enter its final, degenerate era. The galaxy will become a silent, dark graveyard of stellar remnants. It will be a collection of cold, dead black dwarfs, neutron stars, and black holes, all slowly orbiting a central supermassive black hole in the profound, absolute darkness. Over even more unimaginable timescales, these remnants will themselves decay or be consumed. The black holes will slowly evaporate through a process known as Hawking radiation. This is the ultimate quiet at the end of time. A universe that has returned to a state of near nothingness, a cold, dark, and expanding emptiness. This is not a vision to be feared, but one of ultimate peace. It is the final, serene letting go, the last, slow exhalation of a universe that has lived its long and beautiful story. It is the end of the journey, a return to the silent, peaceful darkness from which all things first emerged. Our long journey through space and time is now coming to a gentle close. We have travelled to the galactic core and to the edge of the universe, from the dawn of time to its final quiet end. Now, in this final chapter, we bring our focus all the way back. Back to this room, back to this moment, and back to the profound and beautiful connection between the vastness of the Milky Way and the quiet miracle of your own peaceful presence. If you were to step outside on a clear, dark night and see that faint shimmering band of the Milky Way, you would no longer see just a cloud. You would see the galaxy for what it truly is. That soft light is not distant and abstract. It is a real, physical presence, arriving here, at your eyes, right now. It is the combined, ancient glow of billions of suns, each with its own story, its own potential for worlds. That light has travelled for thousands, and tens of thousands, of years across the quiet emptiness of space just to end its journey with you. It is a direct, tangible connection to everything we have explored tonight. Within that faint glow is the light of stellar nurseries where new suns are being born, and the fading light of ancient stars that have been shining since the dawn of time. You're seeing the crowded, brilliant light from the direction of the galactic core, and the silhouetted shapes of dark nebulae blocking the view. You're seeing the grand design, the starry population, and the echoes of the past, all at once. That faint river of light in the sky is not something separate from you. It is the city you live in. You're looking at the structure that holds you, that carries you, and that has given you everything you are. The connection between you and the galaxy is not just visual, it is deeply, profoundly physical. Every atom in your body, with the exception of the hydrogen, was forged inside a star. The carbon that forms the backbone of your DNA, the oxygen that fills your lungs with every slow breath you take, the calcium that gives strength to your bones, the iron that allows your blood to carry life through your veins. None of these elements were created in the Big Bang. They did not exist in the early universe. They were created slowly and patiently over billions of years in the hearts of stars that lived and died long before our sun was ever born. They were made in the nuclear furnaces of sun-like stars and in the spectacular final explosions of massive supernovae. That material, this precious stardust, was then scattered across the galaxy, enriching the clouds of gas that would one day form our solar system, our planet, and you. You are, in the most literal and beautiful sense, a child of the Milky Way. You're not just living in the galaxy is living in you. The substance of your physical being is a collection of ancient recycled stellar remnants. You're a small, temporary and wonderfully conscious piece of the universe, gifted the opportunity to awaken and contemplate the grand cosmic story that created you. As you lie here, feeling the gentle weight of your body, know that you are feeling the weight of ancient stars, a direct physical link to the grand cosmic cycle of life and death that powers our galaxy. Let us take this connection one step further, to the simplest and most essential substance we know, water. A simple glass of water is a profound cosmic object. The oxygen in every single water molecule was created inside a massive star that exploded billions of years ago. But the hydrogen is much, much older than that. The hydrogen atoms in that water and in your own body are primordial. They were created in the first few minutes after the Big Bang, 13.8 billion years ago. These hydrogen atoms are the oldest things you will ever touch. They have existed for almost the entire history of the universe. They were once part of the great, formless clouds from which our galaxy first condensed. They were part of the first stars. They have been cycled through nebulae and the atmospheres of alien worlds. And now, for a brief fleeting moment in their unimaginably long story, some of them have come together to be a part of you. This simple, grounding fact connects you not just to the galaxy, but to the very beginning of everything. The most mundane and familiar things around us are imbued with a deep and quiet cosmic history. The universe is not just something out there. It is in the air you're breathing, the water you drink, and the very substance of your being. As you rest here, feel the gentle, constant, and reassuring pressure of gravity. It is the force that holds you in your bed, that gives weight to your blanket, that keeps the very atmosphere of our planet from drifting away into space. This gentle, familiar pull is a local expression of the most fundamental and far-reaching force in the entire cosmos. It is this exact same force of gravity, operating on a vastly grander scale, that holds the moon in its orbit around the Earth. It is gravity that holds the Earth and all the planets in their graceful dance around the Sun. And it is gravity that holds the Sun and its 400 billion stellar siblings in their long, slow orbit around the centre of the Milky Way. It is the great silent sculptor, the force that pulls matter together to form stars, that holds galaxies together in clusters, and that weaves the entire web-like structure of the universe. The gentle force you feel holding you now is your own personal, intimate connection to the great cosmic architect. It is a universal, comforting embrace. It is the quiet, unseen power that holds you and your world and your galaxy all together in a single, beautiful and interconnected whole. As you let your body sink deeper into rest, you're not just succumbing to tiredness, you're yielding to the most ancient and fundamental embrace in the entire universe. The space between the stars is a place of profound and almost absolute silence. There is no air to carry sound, only the quiet, invisible hum of cosmic rays and the faint hiss of primordial radio waves. It is a silence of immense and peaceful scale. As you lie here, in the quiet of your own space, you can find a reflection of that cosmic peace. Listen for a moment to the sounds around you. Perhaps there is the soft hum of a fan, the distant sound of a passing car, or just the gentle, rhythmic sound of your own breathing. Your world is not perfectly silent, but it is, hopefully, a place of peace. The quiet of your room and the great silence of the cosmos are not so different. They are both a gentle backdrop against which small, quiet events can unfold. The silence of space allows the faint light of distant stars to travel for eons, uninterrupted. The quiet of your room allows your mind to let go of the noise of the day and to drift, uninterrupted, into a state of rest. In this moment, as you settle into your own peaceful quiet, you are mirroring the serene and silent nature of the vast, starlit spaces we have been exploring tonight. We have journeyed through timescales of billions and even trillions of years. We have contemplated the slow, patient assembly of our galaxy, the long lives of stars and the deep, deep future that awaits. Holding this immense cosmic perspective, even for a moment, can have a wonderfully calming effect on our own human concerns. The worries, stresses and anxieties of our daily lives can feel so large and so immediate, but when placed against the backdrop of galactic time, they reveal themselves for what they are, fleeting, temporary moments. The problem that occupied your mind today is a tiny flicker in the grand, slow and steady rhythm of the cosmos. The galaxy has been here for over 13 billion years, and it will be here for trillions more. Its silent, steady presence is a quiet reassurance that the universe is vast, stable and patient. This perspective is not meant to diminish the importance of our lives, but rather to free us from the weight of our temporary burdens. It gives us permission to let them go, to allow them to shrink and fade into the vast, serene and silent context of cosmic time. As you drift towards sleep, allow your own personal timescale to dissolve into the slow, deep and peaceful river of galactic time. There is nothing to rush towards and nothing to solve. There is only this quiet, peaceful moment of rest. There is a gentle, philosophical idea that is beautiful to contemplate as we near the end of our journey. In some sense, a universe that is not observed, that is not witnessed, is an incomplete one. The stars shone for billions of years before there were any eyes on Earth to see them. The galaxies danced their slow, gravitational waltz in an empty theatre. the entire vast and complex story of the cosmos unfolded in profound, silent solitude. But then, on a small rocky planet in a quiet suburban arm of one particular galaxy, something remarkable happened. A part of the universe became aware. Through us, the universe has developed eyes to see its own beauty, a mind to understand its own laws, and a heart to feel its own wonder. Your own consciousness, your own quiet contemplation of the Milky Way tonight, is not a passive act. It is an active and incredibly meaningful part of the cosmic story. You are the universe's way of knowing itself. The stardust from ancient, long-dead stars has been assembled in such a way that it can now look back out at the stars and understand where it came from. This creates a profound and beautiful closed loop. The cosmos gives rise to the observer, and the observer, through the simple, quiet act of paying attention, gives a form of meaning and reality to the cosmos. Your awareness, as you lie here, is a small, flickering candle of consciousness, but it is enough to illuminate the entire vast, dark and beautiful expanse of the universe. And so we return to where we began, that faint, shimmering river of light across the night sky. But it is no longer just an object to be observed. You now know that it is your home, your origin, and your destiny. You understand your own quiet address in its suburban arm, your long, slow journey around its brilliant core, and the deep, ancient history written in its starlight. You know that the very substance of your body is woven from its recycled stars, and that the gentle gravity holding you is the same force that binds the galaxy together. The Milky Way is not something external to you. It is the grand, cosmic ecosystem of which you are a small but integral part. You're not just looking at the river of light. You are a thinking, feeling, dreaming drop of water within that great celestial river. As you now prepare to let go and drift into sleep, know that you are doing so as a true citizen of the cosmos, a conscious part of this vast, beautiful and serene city of stars. You are peacefully at rest, right where you belong. Tonight, we have drifted through the quiet avenues of our home galaxy, from the ancient stars in its halo to the sleeping giant at its heart. We have felt its immense scale, its deep history, and the endless gentle possibilities held within its trillion worlds. And we have discovered that the vastness of the cosmos is not something cold and distant, but is intimately connected to the quiet reality of your own being. The iron in your blood and the calcium in your bones are the legacy of long-dead stars. The gentle pull holding you softly in your bed is the same force that orchestrates the dance of galaxies. You are made of stardust, held by starlight. You can now let go of this narration and let go of the day. There is nothing more you need to learn or do. You have permission to drift, to rest, and to sleep. The great, silent river of stars will continue its slow, majestic journey, holding you safely as you dream. Sleep well, cosmic wanderer. If you have found a moment of peace here tonight, I hope you will join me again on another journey. Perhaps next time, we can drift through the strange and beautiful worlds of our own solar system, or sink into the quiet, deep mysteries of the ocean. Until then, I wish you a night of deep and restful sleep.